Okay, so welcome to this lecture on divide and conquer algorithms. So in this lecture, we are going to be talking about algorithm design strategy. So what is an algorithm design strategy? So an algorithm design strategy is a strategy that's common to many different algorithms. And so it's something to consider when you are looking at a new problem which hasn't been considered before, for which there are no efficient algorithms. So let's talk about divide and conquer. As a strategy, you must have seen divide and conquer algorithms in the past. So what's the strategy look like? To motivate this, let's look at an algorithm we've already encountered, and that algorithm is merge sort. We encountered this in the very first weeks of this specialization. And what is the purpose of the merge sort algorithm? Well, the purpose of merge sort is to sort an array in ascending order, let's say, and let's say it's an array of numbers. Okay, and given an array of n numbers, the way merge sort worked was, here is an array of n numbers. You split this array into two parts. You split it into two parts, and each part, let's assume n is even, so it's two equal parts. Then each part is n over 2, and then you sorted each of them recursively, and here's where the recursive magic happens. Well, which means what? Which means that you're recursively calling merge sort back on arrays of size n by 2, which itself would secretly call merge sort back on arrays of size n by 4 until you hit a base case. The base case happens when n is really small, like 1 or 2. We have been through all of this, and you know how this process works, so I'm not going to really get much more deeper into this since we have already studied this in the past. All right. And then comes the final output. So here is the sorted output for the first half of the array. Here is the sorted output for the second half of the array. And then we combine. And the combine step is the merge step. In this case, it's the merge step. And when we combine, we get the sorted output for the original problem. So for the original problem, we get the sorted output, whereas each of these recursive subproblems get solved by a recursive call to merge sort. Okay, so this pattern keeps recurring a lot, and you will see this pattern again and again and again this week. And you would see this pattern, for example, to come up with some simple algorithms for solving something like called the max subarray problem. We'll look at the same pattern for multiplying two numbers. We'll come up with an efficient algorithm for multiplying two numbers. Okay, we'll look at something called fast Fourier transform. And we will see the same pattern recurring. And what is this pattern? This pattern is to take your original input and divide it into some number of subproblems. Okay, solve each of these subproblems recursively, get the outputs of each of these subproblems, and combine these outputs. And that will give you the output of your original problem and output of your original problem. So this is going to be the general strategy for divide and conquer. Okay. And now there are different kinds of divide and conquer algorithm, and typically the work is done typically in dividing. So the division step may need some work. Sometimes the division step is trivial. Sometimes the combining step may need work. Sometimes both steps may need work. As an example, in merge sort, going back to this, the division step is actually trivial, theta 1, because you're simply just dividing an array right across the middle, and you're saying just one half, another half. That's just a very, very simple strategy, and that's just theta 1, constant number of operations. The work is done here in combining. So when you combine, you have to do the merge algorithm, which, if you remember, if you recall, is theta of n. It's as much as the size of the array that you're merging. So that's theta of n. All right. And we saw that the overall complexity of this whole thing for an input of size n was n log n. And we are going to see more details on this today. We're going to see more details. All right. Now, let me contrast it with a different divide and conquer algorithm. We also studied this, and this is the quicksort algorithm. Quicksort has the same structure, similar structure, not the same. So given an array, we use partitioning. using something called the pivot element. So you choose a pivot element, you partition according to the pivot element. And if you choose the pivot element at random, or if you have a clever choice, we did not go through this, but there are some clever ways of choosing the pivot called the median of medians trick. Okay. And using this trick, you can actually choose a pivot that's known to be guaranteed to give you a reasonable subdivision. Okay. I'm not going to go deeper into that. You can randomly choose, and then with high probability, you're going to get good behavior. But in any case, partition divides your inputs into two parts. And here is where we do the work, theta of n work. And then we recurse. Okay. And when we come back with the output, with the sorted output, the combination in this case is trivial. Combine is just theta 1. All right. So this is quick sort. Let me give you a third example. We've already seen this binary search, which is another divide and conquer. Okay. In binary search, you have an array. You have a array, and you're searching for a target element in this array. And what you do is based on how the middle element compares with the target, you narrow down your search into, if your original array is n, let's say into n by 2, at most n by 2. So narrow down. And you do some work here. You do a bunch of comparisons, but it's still theta 1. Narrow down your work, and you're reduced to this problem, which you solve recursively. So even though it doesn't fit this pattern, you see it's still an instance of a divide and conquer algorithm. All right. So today we are going to, in this module, we are going to study more and more divide and conquer algorithms. And we are going to see how to analyze divide and conquer algorithm using something called the master method, which we are going to revisit again. Okay. All right. So that's going to be the agenda for this module. And I hope to see you in the next upcoming lectures. Thank you. See you soon. Bye. Okay, so welcome back. So now we are going to make up a divide and conquer algorithm for what we call the max subarray problem. The max subarray problem. Now, what is this max subarray problem? Well, the max subarray problem is like this. All right. So let us say we have an array A. All right. Let's say 2, 1, 0, 8, 15, 7, -1, 6, and so on. So let's say we have an array. All right. So what I want to do is I want to find, and let's say this array is an array of prices in the stock market. All right. So it starts from 2, 1, 0, and then goes up to 8, 15, not to scale, 7, -1, 6. So like this. And let's say you are a trader. Okay. So let's say you are a trader. So price versus time. And let's say you are buying and selling stocks. All right. So the question is, when should I buy this, and when should I have sold it? Okay, not in a real time, but retroactively. Let's ask the question, when should I have bought this stock, and when should I have sold this stock to create the maximum amount of profit? Profit would be the price at which I sold minus the price at which I bought. But we are not allowed to short sell. What does that mean? So no short sell. What does that mean? You cannot sell something before you buy it. All right. You cannot borrow and sell something and borrow against the future and buy it back later and make good. All right. So no short selling. All right. Which means whenever you have to buy, must be before when you sell. Okay. So in array terms, what does it mean? So in array terms, I want to find two indices, I and j, such that a of j minus a of I, the difference, is the largest. So maximize over all possible I and j, such that I less than equal to j. Okay, I and j are array indices. Find the maximum possible value of the difference between aj and ai.
Okay, so for an array of size 1, 2, 3, 4, 5, 6, 7, 8, there are 8 choose 2 or 8 times 7 divided by 6, or sorry, 8 times 7 divided by 2, that's 28 possible pairs of I and j. So this could be I, this could be j, and if I was 1 and j was 7, then the difference is 6. So what's the maximum? So the maximum comes when I equals 3, where a of I equals 0 in this array, and j equals 5 when a of j is 15. You can verify that's the maximum possible difference that you are likely to get. All right. Now what's a brute force algorithm? Brute force algorithm, or a simple algorithm, is like this. Let I run from 1 up to n, or n minus 1. Let j run from I plus 1 up to n. All right. So let's run the index I and let's run the index j. All right. Two for loops, two nested for loops, and then you can say max difference equals the largest of the current value of max difference and aj minus ai. And to begin with, you can say the initial value of max difference is 0, because whenever you choose I equals j, you will always get a difference of 0. So 0 is always possible. So to begin with, max difference is 0, and then first for loop goes from 1 to n minus 1. It could go from 1 to n, that's no problem. Second for loop goes from I plus 1 to n. It could have gone from I to n, no problem. Okay, and max difference is just updated to be the largest between what's the current value of max difference and the difference between aj and ai. All right, and what is the return? Return max difference. Simple algorithm. Okay, what's the running time of this algorithm? Well, the running time of this algorithm is, it's very easy to count. So this outer for loop runs from n minus 1 steps, and the inner for loop runs from, if the value of I, then it runs up to n minus I steps. So the total sum is summation I going from 1 to n minus 1 of n minus I, which is nothing but 1 plus 2 all the way to n minus 1, written in a funny manner. That's n into n minus 1 over 2, which is theta n squared. Okay, so the total number of times this whole program runs is theta n squared, where n is the size of the array. All right, good so far. So brute force, which is just looking at all possible combinations of I and j, runs in time theta n squared. Question is, can we do better than theta n squared through divide and conquer algorithm? All right, so now we are going to design a divide and conquer algorithm for the max array problem. All right, let's do a divide and conquer algorithm. What's a divide and conquer algorithm? It's going to be very simple. I'm going to divide the array into two parts, okay, left and right. So let's start. So I have an array A of size n. So array A has n elements, A of 1 all the way to A of n. I have an array of size n. All right. Let me partition or divide this algorithm into two parts, A1 through A n over 2, A n over 2 plus 1 to A n. Okay, so this must be n over 2 plus 1, all right, n over 2 plus 1. All right. Now the interesting thing happens, all right. Let me find out recursively the max subarray of the left hand side. Let me find out the max subarray of the right hand side. Okay, there are two subarrays, the left one and the right one. So let me find out the max subarray of the left, max subarray of the right. What do I get? I would get two indices, I1, J1, and then I get the difference A of J1 minus A of I1. Okay, so I don't need this, don't need. And again I get A of J2 minus A of I2 on the right, the maximum subarray on the right. But this only looks at the right and this only looks at the left. I get the maximum subarray. And what should I do? Theoretically, I should just take the max of the two, and I am done. All right. But one of the problems is if I partition an array into two parts, into the left part and the right part, I could get the maximum subarray on the left part, which is by here, cell here. I could get the maximum subarray on the right part. Unfortunately, it could so happen that the real maximum was somewhere like by somewhere in the left and cell somewhere in the right. Okay, so I've only covered two cases. I've looked at the maximum from the left hand side and the maximum from the right hand side. But one of the problems is the problem may not split neatly in that manner. The maximum could simply be that you buy from the left hand side and you sell from the right hand side. Okay, but this case is kind of easy. So what do we do? So to combine, we already have the best solution from the left hand side. So if you entirely restrict yourself to the left, we have the best solution. If you entirely restrict yourself to the right, we have the best solution. All right, so you have the best solution if you entirely restrict yourself to the left or to the right. Now the question is, how do you deal with solutions that straddle the middle? Straddle the middle. There is an easy answer. Okay, so if a solution straddles the middle, there's only one thing that can happen. On the left hand side, you take the minimum element. On the right hand side, you take the maximum element. So you take the max of the right hand side and you take the min of the left hand side. All right, so what does it mean? So I'm going to go through the left hand side and I'm going to find the smallest element here. I'm going to the right hand side, I'm going to find the largest element here. Okay, now what I have to do is I have to consider that as a third possibility, not just two possibilities. In my combine step, I need a third possibility. What is the third possibility? Third possibility is in my combine step, I also look at the max of the right hand array. So the right hand array goes from n by 2 plus 1 to n minus the min of the left hand array. And the left hand array goes from 1 to n by 2. Okay, so this, and then I look at three solutions. Solution number 1 is the best solution from the left hand side. Solution number 2 is the best solution from the right hand side. Solution number 3, which I computed specially for the combined step, and this is not divide and conquer. This is just a linear scan of the array. I'm scanning the array, finding the smallest element on the left. Scanning the array, finding the largest element on the right. And I take the difference between the largest on the right minus the smallest on the left. And these are the only three possibilities you have. Okay, and therefore, whichever is the max among these three solutions is the answer to my original problem. Okay, so let me recap. Divide and conquer has three steps: divide, recursively solve the problem, divided problems, and combine. Here, divide is very simple. If you have to find the max subarray of an array A, divide it into two parts, from left, A from 1 to n by 2, and right, A from n by 2 plus 1 to n. And note that because the video has been mirrored, what is right for me may actually be left for you. What is left for me may actually be right for you. All right, so unfortunately there is a flip over and I don't keep that in mind. But in any case, there is 1 to n over 2, n over 2 plus 1 to right, to n. Now you recursively solve for 1 to n over 2. You get the best solution that only involves the first half of the array. Okay. Then you get a recursively solve this from n by 2 plus 1 to n. You get a solution that's only good for the second half of the array. But we convinced ourselves that that's not necessarily everything that could happen. Either your solution is entirely contained in the first half of the array, entirely contained in the second half of the array, or it has to straddle. It has to straddle the two halves. If it's straddling the two halves, there's only one possibility. The minimum side must be on the left, the maximum must be on the right. Otherwise, you get a negative answer. That's not possible. All right. The minimum on the left must be the smallest number from 1 to n over 2. The maximum on the right must be the largest number from n over 2 plus 1 to n. So you might as well find that solution. Use that as a third possibility. Whichever one is the maximum among the three, because we are interested in max subarray, you take that maximum and that's the answer. So divide, recurse, combine. All right. So in the next step, I'm going to write the pseudocode for this algorithm for max subarray problem. Okay. And I'm going to do the recursion for the running time of the max subarray problem. I'm going to look at the max subarray problem, and we are going to write down the pseudocode for max subarray. So I'm going to write a function max subarray given an array A, given a left hand limit L, and given a right hand limit U. Find the max subarray for the part of the array going from AL to A sub U. Okay, so that is the problem. All right, so this is a unnecessary bracket right there. All right, so that's the problem. Find the max subarray for the part of the array that goes from A sub L to A sub U. All right, now what's the base case? Well, if the base case is if U equals L, if the subarray is really small, it just has one element, right? What do you need to do? If the subarray just has one element, then it's really the max subarray is 0. There's nothing much you can do. All right. Else, if the subarray has two elements, then the max subarray is what? So if I have an array of two elements, A and B, then the max subarray is either B minus A if B is greater than A, or it's 0. All right. So let's do that. If U equals L plus 1, then it's either max of A of U minus A of L, or 0. So this is return, this is return. This is very simple. If the array has one element, two element, use your imagination. How do you solve the problem for trivially small arrays? Very good. So that takes care of the base case. Otherwise, what do we do? Otherwise, we do the following. Otherwise, the array has at least two elements. Let's compute a midpoint. Let's call this L plus U divided by 2. In Python, that's slash, so I'm reminding you that integer division divided by 2. So that's the midpoint. All right. Now I can call max subarray. So let's call it M1 is max subarray of A going from L to M. M2 is max subarray of going from M plus 1 to U. All right, so we have A going from L to M, M plus 1 to U. What else do we need? Well, we need the third part. So this takes care of the optimal solution for the first half of the array. This takes care of the optimal solution for the second half of the array. Now we have to compute the case for straddling. What about straddling? Well, let's say y1 is the max value, maximum element of A from M plus 1 to U. X1 is the minimum element. We are going to implement this function in a bit, of A from L to M. So take the smallest in the left, largest in the right. What is the return value? Return the maximum, whatever is the maximum between M1, M2, or Y1 minus X1. Okay, so return whatever is the maximum between these three, and that's the answer for the original problem. So that's the pseudocode, and this is for the straddling case. And together with step number, let's call this 1, let's call this 2, these are the base cases, 3, 4, 5, 6, 7, 8. So step number 6, 7, and 8 are the combined steps. This is the recursive step, and this is the divide step. All right, and on the top is the base case. So that's the entire pseudocode, except for one thing. We still need to know how do we compute the max element or the min element of an array. Very simple. Let's do that. Min element and max element you should be able to write down from L to U is simply, let's say the min element is already, let's start with the min element being plus infinity, okay, a really large number, and then you say for I going from L up to U, okay, min element, okay, ELT, min element equals min of whatever is the minimum of what min element already is and A of I, and return min element. Same for max element except replace min by max. All right, so that takes care of min element, and I have told you that max element is in a similar way. All right, so that's the pseudocode. What about the running time? How long does it take to run for an array of size n? So I'm going to assume that U minus L equals n. Okay, so let's say that's the size of the array. In fact, size of the array region is U minus L plus 1, and let's say that's equal to n. All right, so how long does this algorithm take? Okay, so there is the base case. So base case is when n is less than or equal to 2. So t of n is the running time of this algorithm. So t of n is, let's say, theta of 1 if n less than equal to 2. And that's this part. This is constant, theta of 1. How about step number 3, dividing L plus U by 2? That's a constant. Let's call it theta of 1. Now what about calculating max subarray for the half of the array? Well, if for the whole array it's t of n, for half of the array it must be t of n over 2. If t is the thing that counts, then t must count for half the array. Again, for half the array it must be t of n over 2. How much work does it take to compute the max element for an array of size n over 2? Well, as much time in the worst case as this entire for loop, which is going to run through every element of the array. So it runs through entire array. All right, because it runs through the entire array, this is going to take n over 2 steps, or again in our famous fashion, this is theta of n, this is also theta of n, and computing this max of 3 numbers is theta of 1. All right, so what about if n is greater than 2? Then t of n is, let's add up all these steps with the dot and circle around it, dot and circle, dot and circle, dot and circle. What do you get? So t of n is twice t of n over 2 plus theta of n. Well, it's theta of n plus theta of n, twice theta of n, twice theta of n, plus 1, 2, 3 theta of 1, something like this. But if I take twice theta of n plus 3 theta of 1, this is nothing but big theta of n. Okay, you don't need to worry about the constants. You don't need to worry about theta of 1 when there is a theta of n. All right, that's why we love this big theta notation. All right, so t of n becomes theta of 1. This is the base case for my recurrence to find the worst case running time. Worst case running time. Okay, worst case running time. Otherwise, it's twice t of n over 2 plus theta of n. All right. In fact, what you will end up finding is this is exactly same recurrence as merge sort. So we run this max subarray algorithm in theta n log n time. And this is a much faster algorithm than the brute force algorithm we started with. The brute force algorithm was theta n squared. So how does n squared relate to n log n? Well, for really large n, let's say 10 to the power 6, n squared is 10 to the power 12. So n squared is fast growing. So 10 to the power 12, this is n squared. What about n log n? N log n is almost linear. It's just a slightly curvy line. and that's about 6 times 10 to the 6. Okay, so if it's log to the base 10, it's usually log to the base 2, which is slightly larger. All right, so here we have a big difference. You have the algorithm being about 1,000,000 times faster. Million times, is that million? No, one more zero, faster. So this divide and conquer algorithm we just gave you is 1,000,000 times faster for an input of size million. For an input of size trillion, it's even faster. It's about 1,000,000,000,000 times faster. Okay, and that is saying something, right? So that's saying something. So these algorithms are going to be very, very efficient sometimes compared to even an n squared algorithm, right? Okay, so that's the max subarray problem. We saw how a divide and conquer algorithm works, how to write the pseudocode, how to write the recurrence. All right, now how to solve the recurrence is going to be a topic which we are going to come to later, but let's look at one more example of a divide and conquer algorithm coming up in the next lecture. See you then. Bye. And now we are going to talk about addition and multiplication of big numbers. So what are big numbers? All right. So in a computer, you are able to write down numbers that are up to, depending on number of bits in your computer when you purchased it. In a modern computer, you are able to do 64 bits, and that's called the word size of your computer. Okay, word size means that your processor, your CPU, central processing unit, at any single step can add or subtract or multiply or divide two 64-bit numbers. All right, two 64-bit numbers. Now suppose we were interested in numbers much bigger than 64 bits. All right, the question is, how do we add or subtract or even represent these numbers? All right, so the first thing is, let us imagine there are two numbers a and b which are bigger than 64 bits. Let's say a is the number 1011 01111. So you can write these numbers as arrays. So these numbers can be written as arrays of zeros or ones, and they have a name. They are usually called bit strings. Okay. Usually what people do is they represent each thing inside a bit string. All right. Often bit strings are strings of characters, and you can store 8 characters at a time, and you concatenate together to form a bit string. All right. But for the purposes of this lecture, we think of them as just arrays of binary bits. So arrays of bits. All right. Now we are going to look at efficient algorithms for adding and multiplying big numbers, knowing that your computer's processor can only do 64 bits at a time. Question is, how do we do it for arbitrarily long arrays of 1,000 bits or 5,000 bits or 10,000 bits? And this is the kind of calculations you often do in cryptography, for example. In implementing RSA, you need this kind of calculation. Lots of languages like Python carry it under the hood using big num, and there is packages called GNU, multi-precision, also called GMP numbers. All right, so there are lots of ways of implementing this on a computer. We are just going to explore some algorithms behind it. All right, now what's the algorithm for adding two arrays? So adding two arrays of bits. So add AB, and let's for simplicity say that A and B are of the same size. Okay, if they are not of the same size, then pad B with enough zeros in the beginning to make them of the same size. So let n be the size of A and B. And the result needs to go into an array called C. And so let me make a new array of size n plus 1 bits. All right, so that's going to be hold my result. All right, so what is the algorithm going to look like? What is the algorithm for addition? Let's go over how addition works for binary numbers. It works exactly the same way it does for decimal numbers, except that you need to imagine that instead of adding zeros and 0 to 9, you're adding things just zeros or ones. Let's add these two numbers. Okay, these are two binary numbers. How do we do it? We go digit by digit starting from the least significant bit. All right. So 1 plus 0 is a 1, no carryover. 1 plus 1 is a 0, carryover of 1. 1 plus 0 is a 1. 1 plus 1 is a 0, carryover of 1. 1. 1 plus 1 is a 0, carryover of 1. 1 plus 1 is a 0, carryover of 1. 1 plus 1 plus 1 is a 1, carryover of 1. The last carryover gets into the biggest position. How do we do that for two arrays algorithmically? So here is how we do it. So here is the pseudocode. For I equals 1 to n, so I'm assuming 1 is the least significant bit, and n, the last element of the array, is the most significant bit. So this is the LSB and this is the MSB or the USB. Let's call it MSB. Okay. So when you write this as a number, it's actually the number 1 1 0 1 1 0 1. So reverse it and write down the number. Okay. So the array is kind of reversed to write down the number. Okay. Be careful. All right. So for I equals 0 to n. All right. So for I equals 0 to n, what do? So we simply say, so we initialize a counter, a variable called carry is initialized to 0. All right. Now I'm going to do carry, comma C of I. Okay. There are two outputs. Is sum up the bits, sum of bits, A of I, B of I, and carry. So if I give you AI, BI, and carry, then the result is whatever needs to go into CI and whatever the new value of carry is. So this is kind of called a simultaneous assignment. It's possible in Python. You're just carrying two assignments out at the same time. And this is implementing exactly the same logic. 1 plus 1 plus 1 should be a 1. 1 plus 1 should be a 0, carry 1. 1 plus 0 should be a 1, carry 0. All right, so implementing exactly the same bitwise. So this is going to be like 8 if then else conditions. Okay, 8 if then else conditions. So I'm not going to write down the sum of bits. It's going to be theta of 1 time. Okay, it's a very, very simple straight line code, but it's going to have 8 cases. I don't want to write down 8 cases. So this is the overall algorithm to add. Set a carry to 0, iterate from 1 to n, and C of I is going from the sum of the bits A of I, B of I, and the existing carry, gives you the new carry and the C of I. There's one last step, C of n plus 1 equals carry. The last carryover must be written at the MSB position of C, return C. All right, so this is the addition algorithm for adding up two numbers. So this is adding up two binary numbers represented by arrays. We assume that the sizes of these numbers are the same. All right, if the sizes of these numbers are not the same, if A has size m and B has size n, can you rewrite this algorithm without making the sizes the same? Can you rewrite this algorithm? I leave it to you as a challenge. Okay, and the idea here is you do this for the common sizes of the two arrays. So for minimum of m and n, whichever is smaller, you iterate through the for loop for that. And then for the rest, for the larger array, you simply copy over, but noting that there is a carry. All right. So that's going to be a challenge for you. I hope you are able to write it. It's a simple algorithm which can also handle arrays of two different sizes. My code just shows you how to handle the array of the same size. All right. So this is the overall structure of the add algorithm. Now what about the multiply algorithm? So what about multiply algorithm? We will see that in the next lecture. Okay, so we have seen the add algorithm. We'll see the basic multiply algorithm called the grade school multiplication. And then I'm going to teach you a much more fancier multiplication algorithm called the Karatsuba multiplication algorithm, which is going to be a divide and conquer. Okay, so I'm going to teach you the divide and conquer strategy for multiplying two big numbers represented as arrays. All right, I will see you in the next lecture where I'm going to talk about the grade school algorithm for multiplying two numbers. Okay, welcome back. And now we are going to look at, we looked at adding two large numbers, and now we are going to look at the problem of multiplying two large numbers. I'm going to start with an algorithm that we all know very well, and this is called the grade school algorithm. All right, so let me set up the problem carefully. What do I need to do? I have two arrays A and B, and these are going to be arrays of ones and zeros. Okay, and they can be arbitrary size. And these are representing binary numbers. Let's say the size of the array A is n and the size of the array B is m. And regarded as binary numbers, I would like to calculate the multiplication of A and B. And how big is the multiplication of A and B going to be? It's going to be m plus n. All right. So I want to compute the product of A and B, which is going to be an array C. I'm going to call this array C, which is going to be of size m plus n. All right. Now, what do we have? So let me assume that we have created a routine called add assign or add to, okay, C, and let me just call it, let me not call it C because we have already used C. Let me call it result. And whatever, let me call this x. Okay, let me call this x. Now these are two arrays. Result is, let's say, of size m plus n. X is going to be of size, let's say, n. And what is this going to do? In binary terms, it's going to assign result to the sum of result plus x. Okay, so this is going to be both the argument and the return. So it's going to accumulate. Okay, so this is going to accumulate. How would you write down such a routine? We've already looked at it in the previous lecture. Okay, so it's important to know how to write this down. We already looked at the basic algorithm for adding two numbers using carryover and so on, and we looked at it previously. Now we are going to do grade school multiplication. Let's do it through an example. How do I multiply two numbers? Let me multiply the number 1101 with the number 101. How is this going to work? And these are binary numbers, okay? So in binary numbers, you only have 0 or 1. So when I multiply 1101 by 1, I get 1101. When I multiply 1101 by 0, I get 0000. And then I get 1101. And then I add. Okay, this is called grade school multiplication. You should have studied this in grade school. And the result is 1000001. All right. Okay, so what is 1101? 1101, you might recognize this as the number 13 times 5, and this is 64 plus 1, which is 65. All right, in decimal, but we are doing binary addition. All right. So what are the important things here? The important things here are, we take one of the numbers. Let's call this number the number represented by the array A. Let's call this the number represented by the array B. We are going through the bits of the array B from the right to the left, from the least significant bit to the most significant bit. All right. And every time what we are doing is we are adding. So we are creating an array called result. Initially, let's say result is, now these are 4 plus 3, 7 bits. So result is a bunch of 7 zeros. Okay. Now what we do is, initially if this is a 1, we add 1101 to the result. The next bit is a 0, so we shift and add nothing. Next bit is a 1, so we add 1101, but with 2 shifts. Okay, so 2 shifts. All right. So in effect, we are shifting and adding 2 zeros at the end. All right. So this is kind of important. So we need 2 operations. So we need this add operation, okay, which is said here, and we need a shift operation. What is a shift operation? A shift operation is going to be, and let's call this the shift left operation. So given an array result, to store the result, and an array x, what it's going to do is, I'm going to copy x into result followed by a 0. So the result is going to be the new value of result is going to be the array X followed by a 0 at the end. So I'm using the notation of this class, so arrays will start with 1, not with 0. Okay, so x of 1 to x of m. So lay out the array X, append a 0 to the end of the array. And return. Okay, so result is going to be the argument which is going to get returned. All right, so these are the two operations I'm going to need. Then what is the code for grade school multiplication? So grade school multiplication is now going to look like this. Okay, so you're going to have two arguments, a and b, and let's use b as the multiplicand. Okay, so now we are going to say for j equals m down to 1. Okay, now what are we going to do? So what we are going to do is, okay, so initially we are going to set result to 0. Result is going to be a 0 array, an array of m plus n zeros. We are going to create an array called temp. Temp is going to be an array with, let's say again m plus n zeros. We don't need that many. All right. Temp is going to save the shifted version of a. All right. So temp is going to save the shifted version of a. All right. So let us say temp equals a. Copy a into temp. All right. So result is 0. Temp is a copy of a. All right. Then for j equals m down to 1, if b of j equals 1, if b of j is 1, then what? Then we do result add to result temp. Okay, add temp to result, and then in any case I'm going to shift temp. Okay, I'm going to shift left temp. What is shift left? Okay, so let me now define shift left properly. So I'm going to replace the shift left as shift left of an array is simply going to be, okay, instead of copying an array, I'm going to save that copy, and the shift left of the array is going to be what? I'm simply going to say res equals res plus a 0 at the end. So if res was, for example, the array 1 1 0 1, its shift left would be, the return would be 1 1 0 1 followed by a 0. If it was 1 1 0 1 followed by a 0, it's going to be 1 1 0 1 0 followed by a 0. So shift left is now going to add a 0 to the end of res, not just add, append. Okay, so it's going to append a 0 to the end of the array. That's all shift left does. So this is going to be the standard grade school multiplication for j equals m down to 1. All right, if the current bit, so j is going to go from the end down to 1. If the current bit is a 1, then add it to the result. Otherwise, in any case, even otherwise, so this is not the else, this is just otherwise, shift the temp array by left. Okay, so temp is going to initially be a, and it's going to be the shifted version of a to the left by 1. All right, now this is a little bit messy, but I will post the code on Moodle. All right, so what do we have from here? What we have from here is that the grade school multiplication algorithm, what's the complexity of it? All right, so the outer loop runs m times. Okay, m times. What about this add operation? Add operation is going to be depending on how we implement it. Let us say this add operation is theta m plus n. Okay, so theta m plus n, and the shift operation is theta, let's say n. All right. So the overall algorithm is going to run in time theta m times m plus n. Okay, something like this. And if m is equal to n, if the two arguments are of the same size, this is theta n squared. All right. So it's a quadratic algorithm. So the grade school algorithm is a quadratic algorithm. It goes down one of the multiplicants and keeps shifting the other multiplicand left and adding it to the result. It's a simple algorithm. Okay. It's a little bit messy when presented on the board like this, but hopefully the notebook that I post will have the details for you to look through the grade school algorithm. All right. So theta n squared is the time required to multiply two n-bit numbers. Okay. So if m equals n, then this is theta n squared. If m is not equal to n, then it's something like theta m times m plus n. All right. So typically we will have the smaller number as the multiplicand and the larger number as to accumulate. All right. Or it could be the other way around too. It all depends on how this add to operation is implemented. Based on that, you will have to decide whether the smaller number is the multiplicand and the larger number is the multiplicand. All right. I will leave this at this because learning the grade school algorithm was not our focus. Our focus was to do better than the grade school algorithm. All right. So welcome back. And now we are going to do a divide and conquer algorithm for multiplication. All right. What's a divide and conquer algorithm for multiplication? All right. Now let's simplify the problem a little bit. We have two arrays A, okay, and B. Something like this. Okay. And let's say both are n-bit arrays. N-bit arrays. And for simplicity, always assume that n is a power of 2. Okay. And why is this assumption important? For now, it's useful to have it. Later, we will relax it. This assumption is useful because we are going to divide and conquer, and we are going to divide n by 2 repeatedly. And each time we do that, let's assume we always get back a whole number. All right. This is not important, but useful in case you are worried about getting fractional numbers when we do divide and conquer. My goal is to compute A times B. Okay. How do I do that? We already saw the grade school method for doing that, but the divide and conquer method for doing that is like this. So let's take this array A, and it's an n-bit array, and the array B, another n-bit array, and let's split them along the middle so that you have n by 2 elements on the left and n by 2 elements on the right. Now let's give names for these arrays. Okay, let's call these arrays something. Let's call this array A1, A2. Let's call this array B1, B2. Okay, so the number A is nothing but 2 to the power, okay, n over 2 multiplied by the number A1 plus the number A2. Okay. There likewise the number B is 2 to the power n over 2, the number B1 plus the number B2. What does multiplying by 2 to the power n over 2 mean? So remember, if you have a binary number and you are multiplying it by 2 to the power 2, that simply means adding 2 zeros. All right. So multiplying a number by 2 to the power k is simply the number A followed by how many zeros? K zeros. So let's recall this. Okay. So multiplying a number by 2 to the power n, because it's a binary number, simply has the effect of adding zeros to the end of the number. Therefore, the number that is represented by the array A, I'm going to use this funny bracket notation for that. So bracket A is the number represented by A is 2 to the power n over 2 bracket A1, the number represented by A1, plus just the number represented by A2. Likewise, bracket B is 2 to the power n over 2 B1 plus B2. And remember, A1 and A2 are half the size of the original array. Therefore, let's do what is A times B. Well, doing this cross multiplication of these two numbers, you will get 2 to the power n A1 times B1 plus 2 to the power n over 2 A1 B2 plus A2 B1. I'm going to ask you to check this, okay, later on your own, plus A2 times B2. This is algebra, okay, just taking these two and multiplying them together and expanding the result out. Okay, I'm going to get this. So in terms of the actual multiplications, multiplying by 2 to the power n of a number is easy. Just pad the number at the end with n zeros, no problem. Multiplying by 2 to the power n over 2 is also easy. Pad it at the end by n by 2 zeros, and these additions are going to be important. All right, so what is the divide and conquer multiplication? So let me write it very simply without really worrying about how am I going to implement the part. So if I had to multiply A and B, all right, what is the idea? The idea is, the base case is if A and B are 1 bits, if length of A equals length of B equals 1, okay, then do a 1 bit multiplication, 1 bit multiply. I'm not going to bother writing that out, okay, but I will post the pseudocode for this. Do a 1 bit multiply, no problem. Otherwise, if they are not 1 bits, then what do? I'm going to recursively split A into two parts, A1 and A2. Likewise, split B into B1 and B2. How do I split this? This depends on how you implement it, okay? I'm not going to go into that level of detail. All I'm saying is split the array into two parts, split the array into two parts. Each part must be of size n over 2, n over 2. Remember that, okay? All right. Now what am I going to do? I'm going to call multiply on A1 B1. I'm going to call multiply on A1 B2. I'm going to call multiply on A2 B1, okay, and I'm going to call multiply on A2 B2 recursively to calculate these four quantities, A1 B1, A2 B2, A2 B1, A2 B2. So I'm going to do these four multiplications, 1, 2, 3, 4. I'm going to do these four multiplications. Sorry that it's getting to the bottom of the board. Hopefully you're still able to see it. All right, 4 multiplications. And then I'm going to do the shift and add. Okay, so I'm going to do the pad. So continuing here, pad the result of A1, B2. Let me call this R1. Okay, pad R1 with n bits. Okay, let me call this R1 again. So R1 is padding R1 with n bits. Then let's call this R2 and R3. So add R2 and R3. Let me call this result R4. All right, pad R4 with n by 2 bits. Okay, and then add, let me call this R5 to be the result of multiplying A2 B2. Then you have R1, R4 and R5. Okay, so a bunch of padding operations and additions. So if I carry out all these additions, then I am done. All right. So what is the bottom line? So this code, if you look at this code, this code is just, what is it doing? It's just carrying out this big expression here is just being carried out. Okay. So what do I need to do? To multiply n bit numbers, what's the bottom line? To multiply n bit numbers I have to do 4 n by 2 bit multiplications. Okay, so to multiply n bit numbers, I have to do 4 n by 2, 1, 2, 3, 4. Or if you look at this expression, 1, 2, 3, 4. I have to do 4 n by 2 bit multiplications, and then I have to do 1 n bit padding, 1 n by 2 bit padding, and what kind of multiplications are these? So this is going to be n bits, so n bit addition, 1 n bit addition, and then 2 n bit addition, 1 n bit addition, 2 n bit addition. Okay. Now this is if n is greater than 1. If n equals 1, you hit the base case, in which case it's just a constant number of operations, theta of 1. Okay, so this gives us a way to write down a recurrence from this algorithm. So this algorithm, this divide and conquer algorithm, leads to a recurrence, and this recurrence is written exactly the same way we have written past recurrences that we have seen. We did it for the max array problem, we did it for the merge sort, so now we are doing it for this multiplication algorithm. So what's the recurrence here? The recurrence here is t of n, the time taken to multiply n is theta of 1 if n equals 1, okay, and if n is greater than 1, it is 4 times t of n over 2, 4 times the cost of multiplying n by 2 bit numbers, plus what's the complexity of padding an array with n zeros, theta of n by 2 theta of n bit add theta of n, 2n bit add theta of n, summing up 4 operations which are theta n. That's the magic of theta, all right, plus theta of n. So this is the recurrence, all right. T of n is 4 times t of n over 2 plus theta of n, all right. And in fact, if you solve it, we'll talk about solving it in a second, okay. If you solve it, take my word for it, you will find that the answer is t of n equals theta n squared, okay. Unfortunately, what happens here is if you solve this recurrence, you find t of n is theta n squared, okay. So you draw the conclusion that divide and conquer multiplication is not helpful. In fact, this is exactly the same complexity, exactly same as grade school multiplication. Okay. Now this is a problem, right? If we had one, the last vector we seem to be defeated because after going through all of this, we came up with theta n squared, the same complexity as grade school multiplication. And now we are going to do better, all right? And the idea here is we are going to knock off this 4 into a 3, all right? Instead of doing 4 multiplications, we are going to do 3 multiplications. And what's that going to do is change the recurrence and change the result, all right? How do we do that? All right, and this trick is called Karatsuba's trick, and the algorithm is called Karatsuba's algorithm. What's the idea here? The idea here is as follows. Okay, let me explain the idea. So we are supposed to do 4 multiplications. Okay, the first multiplication is R1. Let's call this R4. Okay, so R1 is the first multiplication, which is A1 times B1. Okay, R4 is A2 times B2. All right. Now we need to do R2 and R3, right here. Instead of doing that, let's do something else. Let's calculate this quantity. This quantity A1 plus A2 times B1 plus B2. Many students at this point object and say, hey, isn't that the same as A and B, because A is A1 with A2, but remember A is not A1 plus A2, A is 2 to the power n over 2 times A1, which is A1 padded with n zeros at the end plus A2. Here we are just taking the first half of the binary number, the second of the binary number, and just adding them together. Okay, and if these are n by 2 bits, this is n by 2 plus 1 bits. This is n by 2 plus 1 bits. What's the result here? Well, if I multiply this, you observe that this is actually A1 B1 plus A2 B1 plus A1 B2 plus A2 B2. Interestingly, if you notice the middle of this summation, this is exactly what we need here. All right. So in fact, it magically is that sum of these two numbers comes up in the middle, only if I could subtract the last two parts. But I already know the last two parts. So if I multiply R equals this, and I do R minus R1 plus R4, where R1 plus R4 is the sum of the first and the last term here, then that exposes the second and the third term. As simple as that. So there, let me do R3 equals R subtract R1 plus R4. All right. With this, I have a much easier way to compute the middle part. Therefore, the same divide and conquer algorithm can now be reformulated as, what do? We multiply 3 n by 2 bit numbers, okay? Or if you want to be more precise, you multiply 2 n by 2 bit numbers, and then you do one more. Okay, so let me erase this whole thing. Bear with me while I do that. Okay, so let me erase this, and then you do one. If you want to be very precise, you do 1 n by 2 plus 1 bit multiply. But we are going to ignore that it's n by 2 plus 1. What is that n by 2 plus 1? It's just adding A1 and A2, the two parts together, adding B1 and B2, the two parts together. I'm multiplying that. If you want to be very precise, it's n by 2 plus 1, but I will still treat it as n by 2 to make our lives simpler. Okay, what else are we doing? We are doing a bunch of padding. Okay, I won't be as precise anymore. All I am going to tell you is whatever the rest is all theta n operations. So we are going to do padding. So we are going to do add, subtract, a bunch of adds, and these adds are n by 2 bits adds. We are going to do a bunch of single subtraction, okay, and then we are going to do a bunch of padding and more adding, okay, sorry, that rhymes, all right, and a bunch of stuff like that, all right. So if you wanted to write down a recurrence now, the recurrence modifies to, instead of 4, you get a 3, all right. And interestingly enough, it's no longer n squared. What happens? It actually becomes faster than n squared. How much faster does it become? It actually becomes something like n to the power 1.54 blah 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 blah. It's going to become asymptotically faster than n squared. Grade school, okay? In fact, as n increases, this algorithm is going to become much faster than grade school and going to eventually beat grade school. Now you might be wondering, like, where did this number 1.54 blah 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 come from? Well, it's in fact, it turns out to be log 2 to the base log of 3 to the base 2. All right, that's what it is. All right, so in the next step, what we are going to do is look at recurrences of this form, and solve it. Why is that? Because these recurrences keep coming up in divide and conquer algorithm. All right, where are we so far? To recap everything. We looked at multiplication. We looked at grade school multiplication. We saw that grade school multiplication is theta n squared. we thought maybe we could do faster through divide and conquer. We started with divide and conquer by dividing the array into two halves, okay, and trying to multiply them, okay, using algebra. And you found out to your horror that it doesn't change things because there are 4 multiplies of n by 2 bit numbers, and that brings the complexity up to n squared. We used a clever trick called Karatsuba's trick to change that 4 multiplies into 3 multiplies. 2 plus 1, 3 multiplies, and a bunch of add, subtract, padding, all of which is theta n. And therefore, when the dust settles, you get a recurrence which looks like Tn is 3t n over 2 plus theta n. That leads to an answer. Somehow magically Tn equals theta n to the power log to the base 2, 3. So now we are now interested in knowing how to solve these recurrences. So when I come back, we will look at how to solve these recurrences in the next part of this lecture. See you then. Bye.
Hello, and welcome to this lecture on solving recurrences. Solving recurrences, okay, with a focus on divide and conquer. All right, so what is the connection between divide and conquer and recurrences? And we have seen this connection so far already in the divide and conquer algorithms that we have derived. What is the connection? So the connection is as follows. So let us take an example of a divide and conquer or a schematic. So you have an input size n, okay? So you have the input of size n, and typically you divide it into some subparts, okay? And let us say each of these subparts is of size n divided by b. And let us say we have a of these, okay? So normally a and b are dependent on the algorithm. So we have a parts of size n by b each. All right. And then each of these we solve them recursively, and then we have the outputs, the a outputs, and then through the combine step you get the output of your original. You get the output of your original thing, all right, your original input. And this is how divide and conquer works. So you have the original, and then you divide it into a parts of size n by b. You do the recursion, obtain the outputs, and combine to get the final output. All right, so what's the time cost of all of these things? Well, to compute the time cost, we said, okay, the time cost is going to be, well, the time taken to divide. Let's call this f divide, f div of n. This is the time taken to divide for an input of size n. And let's call this f combine of n, okay, which is the, if the original input is of size n, how much work does it take to combine the different parts that this n-sized input produced so that we have the overall complexity. And we learned how to do this. So we learned that the overall idea is to set up a recurrence. Okay, so the overall idea is to set up a recurrence, and when you set up a recurrence, the recurrence starts to look like this. So let me do that. Here is how it looks. So t of n, time taken to process an input of size n, is typically going to be theta of 1 for a base case. Okay, and this is the base case. All right, otherwise it's going to be a times t n divided by b plus f divide of n plus f combine of n. And why a times t n divided by b? Because each of these n divided b, the total time taken is t n divided by b, and I have a of these, so I have a times t n divided by b. F divide n is the time taken to do the divide step, okay, and f combine is the time taken to do the combine step. All right, and this is going to be the recurrence. All right. So now that we have the recurrence and the original, uh, so we have all of this, the base case and the recurrence. Now the question is, how do we solve these recurrences? But before we do that, let me point out some of the cases that we have already seen. So what are the cases that we have already seen? So we have already seen this for a merge sort. Merge sort is you divide your input into two parts and each part is going to be n by 2. So two parts of size n divided by 2 each. Okay, so that is merge sort, and then f divide of n is simply theta 1. There is no work to divide in merge sort, okay, just some bookkeeping. F combine is done through the merge algorithm, and that's theta of n. All right, so therefore you have the recurrence which we have already seen. Okay, otherwise. All right, so this is the recurrence for merge sort. What about max subarray? In fact, it's exactly the same deal in terms of the recurrence. It's exactly the same thing as merge sort. All right, how does that work? All right, so for max subarray we have a equals 2, b equals 2, okay, 2 parts of n over 2, and then f divide is theta 1, okay, f combine is theta of n. Remember, to combine, you took the middle of the array and you computed the max of the right side, you computed the min of the left side. All right, so that was theta of n. All right, so that's the work needed to combine. So therefore you get the same recurrence. Otherwise, okay, same as merge sort. Okay, so what else? We have seen Karatsuba. Karatsuba's algorithm. Okay, what's Karatsuba's algorithm? Karatsuba's algorithm goes like this. What did we do? So we said T of n. Okay, let me first describe the algorithm, right? So what did we do in the algorithm? We took an n digit number or n bit number. We divided it into two n by 2 bit numbers. All right, and interestingly, if you thought carefully, there were three sub problems. So three sub problems: a1 b1, a2 b2, a1 plus a2 times b1 plus b2. There were three multiplication subproblems. Three multiplication subproblems, right? Work to divide was theta n because we needed to do this addition. Okay, so we needed to do two additions to divide. So here you get your first instance of an algorithm where you're doing some work to divide. We will look at more such algorithms. And then you got these three parts, and work to combine was again theta of n. Okay, a bunch of additions, subtractions, and padding. No multiplication though, padding. All right, by shifting and adding zeros to the end. So the recurrence here looked like this. All right,
So this was Karatsuba's algorithm. So the question now is, suppose you have these kinds of recurrences, how do we solve these? How do you solve these? Okay, so that's the all important question that we are now going to address. All right, let's look at how to address the all important question of solving these recurrences. All right. Okay, so let us look at solving these recurrences, right? So let us first do some examples. So let us look at the recurrence that we got for merge sort or max subarray problem. Okay. All right. Uh, so let me start by doing the following. I actually went one step too far. Let me start with the first step, theta of n, big theta of n. Now, one of the things I would like to do is instead of calling it theta of 1, I would simply call it a constant. Let me call that constant C0. Same thing. Instead of calling it theta sub n, theta of n, I'm going to call it C1 times n. Okay. So this constant is going to make my calculations easier, and I am going to be a little bit more rigorous. This is not perfect, but it's at least a little bit more rigorous than what we have been doing so far. All right. So therefore, once I fix this, okay, once I fix this, the recurrence is going to look like this. All right, the recurrence has been fixed. Okay, I have fixed my work. Now, how do we solve this? Okay, here is the standard method that I'm going to use. It's called the expansion method. Okay, it's kind of a technique for solving it, in which I'm simply going to keep expanding this recurrence until I hit the base case. Let's do it like this. So when I have t of n, okay, so I can say t of n is twice t of n over 2 plus c1 times n. All right. Now this is nothing but, let me recursively expand inside. Okay. So twice of t of n over 4 plus c1 n over 2. Okay. So I'm going to expand the inner one. Okay. Remember, if t of n follows this pattern, then t of n by 2 better follow the pattern twice t n over 4 plus c1 n over 2. Okay, so you better have this pattern inside. Okay, plus the c1 n gets copied over. All right, so let me clean this up. Okay, now that I've cleaned this up, you get this. So this, when it simplifies, you get 2 squared, okay, 2 times 2, t of n over 2 squared plus twice c1 n over 2 plus c1 n. And when that simplifies, you have 2 and 2 cancel. Okay, so cancel. Okay, so this is what you get second time around. What about the third time around? So you get 2 squared twice t of n over 2 cube plus c1 n over 2 squared. This is just expanding this term here. Okay, expanding the term again inside plus c1n plus c1n, that's 2c1n. Okay, so what do we get? So we get 2 cube t n over 2 cube plus 2 squared c1 n over 2 squared plus 2c1n. One more step, 2 cube t n over 2 cube plus 3 times c1n. Okay, now this is the result of 3 expansions. Now if I expanded it one more time, I would get 2 to the 4 t n over 2 to the 4 plus 4c1n. This is the result of 4 expansions. What about 5 expansions? 2 to the 5 .
right? So if I did some unknown number, let's say j expansions, I would get, this is just pattern matching, 2 to the power j t n over 2 to the power j plus j c1n. And that's the result of j expansions, right? Now, when do I hit the base case? How many expansions do I need to hit the base case? Base case is t of 1, right? So let me call this 2 to the power j, but this is how much is j required to be so that this quantity here is a 1. So n over 2 to the power j is equal to 1, or generally less than equal to 1, and you will find that j is nothing but log to the base 2 n. Okay, so this is not going to be a whole number often, but if n is a power of 2, this is going to be a whole number. All right, but let us just keep moving, assuming that n is a power of 2. So for now, assume n is a power of 2 so that j comes out to be a whole number. But even if j is not a whole number, there is no problem. We can modify our technique slightly and we will obtain the same answer. Okay, so I'll deal with one complication at a time. So if j equals log to the base 2n, I get to the base case. So this is 2 to the power log to the base 2n times t1, which is c0, plus log to the base 2n, which is j, c1n. So this equals n. So c0n plus c1n log to the base 2n, which is theta n log n. And here I don't need to say the base anymore because every log is just a constant factor of a different log. So once I put a theta, I don't have to say this. So in the end, this is what I get. Tn is theta n log n. This is the solution that I seek. Okay, and this gives me the running time for merge sort and the maximum subarray problem, for instance. Now, what about the more general case where we have t of n is theta 1 if n less than equal to 1, and a times t n over b plus, let's say, theta n to the power c otherwise. Okay, and this is used to be called f of n. Now I'm just making it n to the power c for some c. All right, how do I solve it in the general case? Okay, and this is where a very important method called the master method comes into play. Okay, so what is the master method? So the master method says, let me compare, okay, let me compare epsilon, okay, or let me call this quantity epsilon, equals log of b to the base b of a, okay, versus c. Okay, so in case 1, log b to the base a is greater than c, and this is called case 1. Okay, log of a to the base b, okay, this log is greater than c. In this case, the answer is given as Tn is theta n to the power log to the base b of a. Okay, case 2, the two quantities are equal. In this case, the answer is given by okay, the same n to the power log b of a here times log n. All right, and case 3, just the opposite. Okay, so there's just one case remaining, right? What is case 3? So case 3 is log to the base a b is less than c, then t of n is theta n to the c, n to the power c. All right. So this is basically a shortcut, or basically pre-worked out answers. Okay. And because of these pre-worked out answers, we can actually now try and solve problems that are of interest. Let's take the problem for merge sort that we just calculated. In this case, a equals b equals 2 and c equals 1. Remember? Okay. So pattern match a, b, and c. Okay. So now that you have this, which case applies? So log to the base b a is log to the base 2 of 2, which is just 1. Okay. So and c equals 1. So case 2 applies, and the answer is n to the power log to the base b of a log 2 2, which is 1 times log n, which is n log n. This is exactly the same answer as what we derived a second earlier. Okay, so I hope this is clear, right? I hope this is clear. Let me make it shorter so that we can see the whole thing at a glance. Okay, so what about Karatsuba? Remember, t of n is 3 times t of n over 2 plus theta n to the power 1. So a is 3, b is 2, and c is 1. Therefore, let us say log to the base b of a is log to the base 2 of 3, which is going to be, remember, log to the base 2 of 2 is 1, log to the base 2 of 3 is whatever this number we are interested in, log to the base 2 of 4 is 2. So this number is between 1 and 2, and it's like 1.54 something. Therefore, which case applies? Case 1 applies because log to the base b of a is greater than c. Therefore, t of n is theta n to the power log to the base 2 of 3, which is theta n to the power 1.54 blah 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 blah. Okay. So what is the master method giving us? Well, the master method is giving us some interesting pre-worked out answers that we can apply to the problem at hand. Now let us use the master method for other things as well. Okay, so let us apply the master method to more interesting examples as well. All right, so let's take this master method is being written up here, okay, for your reference. All right, so let us take example number 1. Let us take the naive divide and conquer multiplication. Okay, here I took an input of size n and I produced two inputs of size n over 2. Okay, uh, so and this was I split each of my two inputs as a1 a2 b1 b2, and then I had to do 4 sub multiplications of size n over 2, so 4 sub problems of size n over 2, okay, which were a1 b1 a1 b2 a2 b1 a2 b2, okay, 4 sub problems, combine, and then theta n combination to construct a times b. So a times b. All right, so here t of n was equal to 4 times t of n over 2 plus theta of n. Okay, so here a equals 4, b equals 2, c equals 1. This is n to the power 1. So epsilon log of b
of a, which is log to the base 2 of 4, which is 2, epsilon greater than c. So therefore, case 1 applies, and the result is theta n to the power epsilon, which is theta n to the power 2. All right. So I don't really require you to recall the master method if needed. But what I really would like you to do is make sure that you know how to use master method. And the important things are identifying A, identifying B, identifying C for your problem, and looking at how to use these three cases, which of the cases apply, carefully looking at those cases, and then solving it. Okay, so let's do one last example. Okay, so in this last example, we will look at something called Strasson's multiplication. All right, so the Strawson multiplication algorithm looks like this. Okay, I'm not going to cover it, but it looks like this. So I have two n cross n matrices, and I would like to multiply these two n cross n matrices. And what Strawson does is subdivides each of these matrices into four n by 2 cross n by 2 matrices. Okay, so 4 n by 2 cross n by 2 matrices. And what Strawson then does is if you have 4 n by 2 cross n by 2 matrices, normally you would need 8 multiplications. But what Strawson does is do it in 7 multiplications. So at the end of the day, you would get something like this. T of n is theta 1, of course, if n is less than equal to 1. And then it's 7 times t n over 2 plus theta n squared, okay? Why n squared? Because you're going to add matrices, which is n squared otherwise. Okay, so in this case, what you would find is A equals 7, B equals 2, C equals 2. And what is log B to the A, which is epsilon, log of A to the base B, okay? I'm never careful in saying this, so I say log B to the A, but it's actually log of A to the base B, which is log of 7 to the base 2, okay? Which is, what is it going to be? Well, log to the base 2 of 4 is 2. Log to the base 2 of 8 is 3. So log to the base 2 of 7 is 2.7 something something. So it's going to be closer to 3 than 2. But it's a number between 2 and 3. All right, with that in mind, how does epsilon compare with C? So we know that epsilon is strictly greater than C. And therefore, case 1 applies. Okay, since case 1 applies, it's theta n to the power epsilon, which is theta n to the power log to the base 2 of 7, okay, which is theta n to the power 2.7 something something something. All right, so that's going to be the complexity of Strawson's algorithm. You get that immediately by master method. All right, so this is all about master method. I'm going to post a video on the side about the proof of master method, like why is this true. Okay, it is simply going to be a derivation that we are going to do from first principles. All right, and that's it. All right, if you are interested, I would really urge you to look at that video where I post the proof so that you get an idea of how these kinds of theorems are proved. All right, see you in the proof if you are interested. But I hope it's clear how to use the master method. All right, thank you. Bye.
Hello, and welcome to this lecture on fast Fourier transforms. Fast Fourier transforms are going to be part of our study on divide and conquer algorithms. So we are still studying divide and conquer, okay? But the main thing that we are going to do is to look at a particular divide and conquer algorithm called fast Fourier transform, or we are just going to call it FFT, the abbreviations for fast Fourier transforms. And it's a very, very important algorithm. And it's a very important and very widely used algorithm. And so I'm going to talk about why it is important and why it is widely used in this part of the lecture. And I'm going to give you a brief introduction to complex numbers, and I'm hoping that you know about complex numbers already. If not, there are plenty of great videos, especially by Khan Academy. Uh, and I will try and place links to these videos if possible. There may be copyright reasons where I'm not able to place these videos, in which case I hope you're able to go online and look up some facts about complex numbers. But I'm going to go through them quickly. And So that you get an idea of what complex numbers are for the purposes of this lecture. All right. So let us start with the very first part of this. Let's start with what is a Fourier transform. Okay. Now, again, Fourier transform is a mathematical technique, and it's an idea from mathematics. And the idea is as follows. So suppose we have a signal. Suppose we have signal, and you can think of data as a signal. It can be any kind of a signal, and this is time on the x-axis, and this is the value of the signal on the y-axis. Now, what kind of signals could we be looking at? We could be looking at, for example, commodity prices or stock prices, and that's an example of a signal. Anything that has a trend, right? We could be looking at temperatures at particular location. And that is an example of a signal. Another example of a signal could be the wind velocity that is being encountered by an aircraft as it's flying. That's an example of a signal. Or last but not least, let's look at one more example. And this could be a voice signal. It could be an recording of an orchestra, music, and that's an example of a signal. So signals generally are series of values across times. And we think about, in this class, we think about what are called discrete signals, which means that there are certain sampling times. There are certain sampling times, and we record the value of these signals at these sampling times. And the sampling time interval between two samples, let's call it delta t. Okay, and these are discrete signals, and we are going to write these discrete signals as a0, a1, a2, up to some a sub n minus 1, and this is a list of values, and that's an example of a discrete signal. And we are going to see some examples of these discrete signals, and we assume that the signals go from time 0 to some number time n minus 1, so that there are n values. And beyond this, we are going to assume that the signal just repeats. So we are assuming that we know the signal from 0 to n minus 1. So we know the signal from 0 to n minus 1. It can be negative as well. And beyond that, we just assume that it repeats the same pattern forever. So it repeats the same pattern forever. So it's what is called in mathematics, it's called a periodic signal. And we have observed one time period of the signal. All right. And that's the assumption. And what Fourier, who's a very famous French mathematician, Joseph Fourier, whose name you might have heard, was a French mathematician. He first invented the techniques that we are going to study here called the Fourier transform. And the idea is to write these signals as the sum of periodic sinusoidal signals. So these are sinusoidally oscillating signals. Okay, we will get much more specific in a few minutes. So you look at it as a sum of various sinusoidal frequencies. Let me just join them up so you can actually see what's happening. All right, plus let's say a sinusoidal frequency. And so this is frequency, let's say 10 hertz. This is frequency 5 hertz. And for each frequency, you have an amplitude, and it's the sum of different frequency components, and each of these is called a frequency component of the signal. Now, I do not have the ability to take you through the whole of Fourier analysis, so I'm going to explain what is important. And there is a wonderful video by this YouTube channel called 3 Brown 1 Blue, who have a very or maybe it's 3 blue 1 brown. I will post a link. Okay, and they have a very beautiful exposition of Fourier series and Fourier transforms for you. So what's a Fourier transform? At a very high level, you have the signal, you have these series of values, okay, at various times are from 0 to n minus 1. So you have a0, a1, a n minus 1, and these are the what are called the values over time, or it's also sometimes called the time domain signal. Okay, and you use this technique of Fourier transform or a Fourier transform, okay, at a high level. And Fourier transform is going to translate this into what is called the frequency domain representation. So instead of the x-axis being time, the x-axis becomes frequency. Okay, the x-axis becomes frequency, and you're going to say, okay, there is a frequency component at 0, and that component has some amplitude. Okay, and let's call this capital A0, and there is some other frequency component, let's say at 10 hertz, and this frequency component has some value A sub 10. Let's say there is a frequency component at 100 hertz, and this is A sub 100. And what you're talking about is that your original signal is a combination of various frequency components. So zero frequency component is a component that never changes. So this is just a constant value A0. A 10 hertz frequency component is a component that's going to have 10 oscillations per second. I won't be able to draw sine waves. So this is 10 with amplitude A10. Here is a 100 hertz signal that's going to oscillate much, 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 much faster. If this is 10 hertz, then it's 100 hertz, 10 times faster. And this is going to have component A100. And what you're saying is that the original signal can be written as a summation of these frequency components. And so Fourier transform goes from your original signal as a sequence over time into the frequency components, or sometimes, the musically minded people would call them the frequency harmonics of the signal. Now, there is an inverse operation called inverse Fourier transform, which is going to take us from the frequency components back to the original signal. Okay, at a high level, that's what Fourier transform is doing. Okay, now Fourier transforms are extremely important in any kind of data analysis, especially if you're going to deal with data like voice data, any kind of time series data, really, voice data, like if you're analyzing human voice or voice signals, or image data. So an image can be written as a two-dimensional signal where it's a bunch of pixels, but instead of a signal over time, it's what's called a spatial signal. So it has X and Y, and you can define easily Fourier transforms of images, and now you get frequency components of images. All right, and frequently what we do using Fourier transforms is it gives us a way of smoothing or denoising signals or images. It allows us to analyze the frequency components to look at, for example, we can look at data like oil futures, and we can look at uh, seasonal trends, seasonal trends in this data, and we can do things like seasonally adjust data and so on. So Fourier transform is extremely important. It's widely used pretty much in any kind of image processing technique, in any kind of signal processing technique. And it's very, very important in data analysis as well, to look at data, to understand seasonal trends, to remove, for example, certain seasonal trends, to adjust data according to seasonal trends. You need to know what a Fourier transform is. Okay. But we are not going to look at so much at Fourier transform as a way to compute Fourier transforms rapidly on a computer. So if you're given a signal, which is just a sequence, a list of values, A0, A1 to AN minus 1. So you're given a list of values. I want to rapidly compute the Fourier transform. Okay. And this is a very specific kind of Fourier transform. It's called discrete Fourier transform. For technical reasons, there are lots of kinds of Fourier transforms. This is going to be called the discrete Fourier transform. Okay, and what you get is a sequence of values And according to mathematical convention, we write them in capital letters, capital A0, capital A1 to capital AN minus 1. And this length of the sequence is going to be the same as the original sequence for reasons I will explain in a second. And I want to compute this sequence rapidly. And then there is the inverse sequence. The inverse sequence is called the inverse Fourier transform. So when you do inverse Fourier transform, you go back from the Fourier transform, which are the frequency components, back to the original signal. And usually what you do is sometimes you adjust the frequency components. One very common operation is you throw out high frequency components. So you would say A0, A1 up to AK, and you would throw out all the high frequency components because they are going to be more uh, like noise is going to be high frequency components. So I'm going to zero out the high frequency components, saying there are no high frequency components. And I can do like inverse Fourier transform. And what I would get is I would get a new signal, which is going to be a smoothed version of the original signal. And we are going to see examples of this. This is going to be important. We'll see examples of this. But the main focus of this algorithms class is to do this efficiently using divide and conquer. So we are going to show you how that works. And when you do it efficiently, you get an algorithm called fast Fourier transforms. Okay. So my hope is to explain the divide and conquer and the fast. But given that we are all interested in data science and we are all interested in being data scientists as part of this larger goal of the specialization, I would like to explain a little bit more than how what the book does, rather than just look at one application. I'm going to look at many applications through some of the assignments and through some of the notebooks. All right. Now, one of the problems with Fourier transforms is this. When we do Fourier transforms of any kind of data, even if its data is real numbers like 2.0, 1.2, minus 1.1, even if the data is real numbers, when we do Fourier transform, you will see that what we get are complex numbers 2.0 plus 1.0j, 1.0 plus 2.1j, minus 1.1 plus 2j, and so on. So there is this, these are called complex numbers. These are not real numbers anymore. These are called complex numbers. And this j, and in many math books, it's called I. I'm going to use the Python or the electrical engineering notation where this is called j, is square root of minus 1. Okay, it's a square root of a negative number, which doesn't normally exist, but we give it a name. We give it a name and we call this an imaginary number. Okay, and so we need to look at what are these complex numbers. So for the rest of this lecture, I'm going to briefly give you an overview of complex numbers. So for the rest, I'm going to give you an overview of complex numbers, a very quick overview, unfortunately. And I'm going to give you some, if you're not familiar with complex numbers, I'm going to recommend that you look a little bit more into complex numbers. I will post a few video notes on complex numbers so that you can get yourself quickly familiarized with complex numbers. If you are familiar with complex numbers, you can quickly look through the rest of this. Okay. So what are complex numbers? So complex numbers were invented by mathematicians to give names like for square root of minus 1. And this is the very most important complex number called j. And remember, j squared is minus 1. Okay. Now, the reason we give it, and in some books, remember, this is written as I. Uh, and in most math books, and I have been using the symbol I, but unfortunately, Python uses the symbol J. So in Python and in most electrical engineering texts and engineering texts, we use the symbol J because I is used for current. So we use the symbol J. Um, and electrical engineers really need to use complex numbers because it turns out that when you look at things like alternating current, for example, or when you look at oscillating signals, it's very, very useful to study them as complex numbers. Roboticists use complex numbers. They use a version called quaternions to look at angles. So complex numbers are very, very important in engineering. It would be very difficult to do engineering without complex numbers. So even though we call them imaginary, even though sometimes we call them imaginary, they are quite a bit useful and concrete in a way that is important. So we'll have to study complex numbers. Otherwise, a lot of engineering control theory, for example, relies very, very heavily on complex numbers. So it's used a lot in engineering. It's also used in computer science and signal processing, Fourier transforms. I'm going to explain a little bit. So this is important. All right. So what is complex number then? So a complex number is basically a number of the form a plus b times j. Okay, this is a and b are regular real numbers, and this j is a very special number. It's the square root of -1, which you imagine exists and you give it a name. So it's a plus b times j. As an example, you have complex numbers like 2 plus 3 times j. So this is the number 2 plus 3 times square root of -1. All right. Or 7 plus 8 times j, or minus 2.3 plus 7.6 times j. So these are examples of complex numbers. Okay. They have two parts to them. They have a real part and they have an imaginary part. So the real part is minus 2.3 and the imaginary part is 7.6. All right, here the real part is 2 and the imaginary part is 3. Here the real part is 7, the imaginary part is 8. Okay, so every complex number has two components, a real part and an imaginary part. All right. So for example, the number j itself is written as 0 plus 1j. Its real part is 0, imaginary part is 1. The number 7.5, for example, is written as 7.5 plus 0j, where the real part is 7.5, imaginary part is 0. Or you can visualize complex numbers on a complex plane, and this is called a complex plane, where the real part is written as part of the x-axis and the imaginary part is written as a y-axis. So every complex number is a vector. For example, x plus y times j is this coordinate x comma y in this plane. I hope this is clear. Okay, and every complex number can be regarded as a vector with x and y as the coordinates, where x is the real part and y is the imaginary part. Okay. Now, using complex numbers, we can add, subtract, multiply, divide complex numbers. How does that work? Let me just give you quick examples. So if I have x plus yj, and then I have x hat plus y hat j, then the addition of these two complex numbers is simply x plus x hat as the real part plus y hat j. So you just add the two real parts to get the real part, and then you add the two imaginary parts to get the imaginary part. That's addition. What about subtraction? Subtraction is very simple. It's exactly the same as addition, except you subtract. Equals x minus x hat plus y minus y hat j. Now comes a slightly more interesting operation called multiplication of complex numbers. So let's multiply x1 plus y1j with x2 plus y2j. And what you get is something like this. x1, x2, you just do algebra, plus y1, y2j squared plus x1, y2j plus x2, y1j. You just multiply it as if j, it's just algebraic manipulation. You just multiply it as if it's a polynomial. And now comes the cool part. J squared, remember, is -1. So this is x1, x2 minus y1, y2 plus x1, y2 plus x2, y1, j. Okay, so this is the multiplication of complex numbers. It is more complicated It's not simply multiplication of x1, x2 and multiplication of y1, y2, because you have to understand that j squared is -1. So this is how you multiply complex numbers. I hope this is clear. Okay. Now, another operation is whenever you have a complex number, x plus yj, okay, let's call this a complex numbers. We usually write complex numbers using z or z1, z2 like that in mathematics. There is a related complex number called z bar, which is the complex number x minus yj. And this number has a name. It's called the complex conjugate. And it has a very important property. So the complex conjugate has the same real part, but then the imaginary part is just negated. Okay, that is called a complex conjugate. And now you have something important. When you multiply a complex number with the complex conjugate, you get the following. So you get x plus yj times x minus yj. You can take a second and derive it for yourself if you are interested. But what you get is something very, very nice. You get x squared minus y squared j squared. All right. And you get, sorry, x squared minus y squared j squared. So you get x squared plus y squared. Okay. So multiplication of a number, and then there is no imaginary part. No imaginary part. It's just a real number. So multiplying a number with its complex conjugate just gives you x squared plus y squared. This is important because what you can interpret this complex conjugate in the following way. So suppose you have x, y, complex number x plus yj, then its complex conjugate is just this number. So what you do is you reflect the number around the real axis. You reflect the vector around the real axis. So if you take the reflection of the vector around the real axis, the complex conjugate is simply x minus y. So this is the complex conjugate. It's just the reflection around the real axis of the vector. And this angle is theta. This angle is minus theta. All right, so it's just the reflection around the real axis gives you the complex conjugate of a number. And this x squared plus y squared, this x squared plus y squared has an interpretation. It's the square of the length of this vector. So if the length of this vector is L, then this is actually L squared, the square of the length by Pythagorean theorem. So remember, this is y, this is x, the hypotenuse, this is 90 degrees. So the hypotenuse is square root of x squared plus y squared. That's the hypotenuse squared. And this, remember, is the complex conjugate. So square root of z bar equals the length of a complex number or a complex vector. And this has a name. This is called the modulus or the absolute value of z. So this is called the absolute value or the modulus of a complex number. Okay, and that's just the length of this vector, and that's just square root of x squared plus y squared. So to give you an example, let's take the complex number 8 plus 10j. Its modulus is square root 8 squared plus 10 squared, which is square root 164, whatever that is. Okay, so it's going to be 12.9 something something. That's the modulus of this complex number. And if you plotted it, that would be the length of the vector, the length of this vector. And that's called the modulus of a complex number. All right, and this is going to be important. All right, so this is called the modulus of a complex number. And let's now talk about division of two complex numbers. So suppose I wanted to divide z1 divided by z2. What I simply do is I multiply, and I'll assume that z2 is not the complex number 0 plus 0j. Otherwise, you cannot, division by 0 is not allowed, right? So z2 cannot be 0. Assuming z2 is not 0, I can multiply okay, like this. So this is just 1 by the modulus of z2 the whole squared times z1 times z2 bar. So I can define division in terms of multiplication. So as an example, let me do an example. Let's take the complex number 1 minus j and divide it by the complex number 1 plus j. So what's this? So it's 1 minus j times, let's take the conjugate of this number, which is 1 minus j divided by 1 plus j times 1 minus j. So this is just the conjugate. This is z2, then this is z2, this is z2 bar, this is z1, this is z2 bar. I'm just multiplying and dividing by z2 bar. And now this is on the numerator, it's I get 1, okay? And then this is minus j times minus j is plus j squared. And then I get 2 minus 2j on the numerator. On the denominator, I get 1 squared minus j squared. And so when the dust settles, I get 1 by 2 times this becomes 1 and minus j cancel, minus 2j. And so this is minus j. So the division of the complex number 1 minus j divided by 1 plus j yields the number minus j. All right. So this is interesting. This is interesting that you can divide complex numbers this way. Okay. So you can divide complex numbers this way. And this is, very much, so you can divide complex numbers, you can multiply complex numbers. Okay. So complex numbers are very interesting this way. But this is not the main reason they are interesting. The main reason they are interesting is a theorem. It's a theorem by Gauss. Okay. Carl Friedrich Gauss was a very, very famous mathematician who lived in the 19th century. And the theorem by Gauss says that if you have any polynomial equation, then you know that there are exactly n roots in complex numbers. Let me give you an idea of why this theorem is important. So let us take polynomial equations. Let's take the equation x squared equals 1. It's a very, very simple equation. And this has two roots, x equals plus 1 and x equals minus 1. So this has two roots, two real roots, x equals plus 1 and x equals minus 1. But there are some equations which do not have two real roots. For example, let's take this equation, x squared equals minus 3. Now, the interesting part is there are no real solutions, because if you take any real number, x squared, it's going to be greater than or equal to 0. How can it be equal to minus 3? But there are two complex solutions. So you have minus square root of 3j, and then you have plus square root of 3j. You have two complex roots. Likewise, you can take a cubic equation, x cubed plus 3x plus 2 equals 0. I'm not going to try solving it, but you can show that there are three roots for this equation. Okay. And what you can show that these roots can be real or complex. Okay. But what Gauss's theorem says is if your degree of the equation is n, and of course a n not equal to 0, then you'll have to have n complex roots for this kind of an equation. It has to have n complex roots. All right. Now this is why complex numbers became very, very important, because any polynomial of degree n will have n complex roots. And in mathematical terms, this is super important. But they became more important because now if you take an equation like this, x cubed equals 1. Okay, so let's take this equation, x cubed equals 1. So what are the possible roots of this equation? So you can say x equals 1 is a root of this equation. All right. So x equals 1 is a root of this equation, and that's just one of the roots of this equation. Okay. Now, what it turns out is there are two more roots of this equation, and those are going to be complex roots. Okay. So those are going to be complex roots, and there are going to be two more. By Gauss's theorem, I know there are going to be two more complex roots. What are they? Okay. So what you can show is that there are two more complex roots. I will try and write down what those roots would be. So it would be something like minus 1/2 plus square root of 3 over 2j. Okay, so that's an example of a complex root, and we can verify that if you took the cube of this number, you would actually get -1. How would you verify that? I will leave the verification out for later. All right. Uh, okay. So I hope this is okay, and we'll talk about this. We'll talk about this in more detail. So hold on to this, but I will show you that there are three roots of this equation, and these are called roots of unity, and they are going to be super important. They're going to be super important. Likewise, the equation x power n equals 1 will have n roots. Okay, and I'll show you what those roots are. As an example, x to the power 4 equals 1 will have 4 roots. We know two of those, x equals +1 because +1 to the power 4 equals 1, and x equals -1 because -1 to the power 4 is also equal to 1. Now, what are the two other roots that you can have? Okay, the two other roots you can have here, they are very simple. X equals plus j and x equals minus j. Because remember, plus j to the 4 is just j squared, the whole squared, which is just -1 squared, which is just 1. And minus j to the 4 is -1 to the 4th, j to the 4th, which is just 1 times 1, which is 1. So it turns out you do have 4 roots, +1, -1, plus j, and minus j. So these are the 4 roots. So if you go into complex numbers, you get more roots than just one. All right. Now let me get to the last fact about complex numbers, and this is one of the most fascinating set of facts. So recall that, and I'm going through really fast. I'm going through this really fast. And if you need more time to study complex numbers, I suggest that you look through some of the videos to get yourself more familiarized with complex numbers. But let me show you one last fact about complex numbers. So remember, we had every complex number can be written in the complex plane. This is the real part. This is the imaginary part as in terms of its coordinates. And this is the complex number x plus yj. It can be written as the coordinate x comma y. And these are called rectangular or rectilinear coordinates. There is another way to write it. Another way to write it is to look at the length, which we already knew is the modulus of this complex number. If you call this z, this is the modulus of z, which is the same as square root x squared plus y squared. So that's the length of this vector. And there is one more piece of information I need to give you, which is the angle. And angles are always measured counterclockwise, starting from 0. So this is 0 degrees, coincides with the real axis, and counterclockwise until you get to, and you measure angles in radians, and 2 pi radians, which is 360 degrees, equals, you come back to the original point. Okay, and likewise you can say negative angle. So if this is the positive angle theta, then if you go clockwise you get the negative angle minus theta. You can also write minus theta as 2 pi minus theta or 360 minus theta if you're working in degrees. We rarely work in degrees because this is going to be useful to work in radians. I hope this is okay. I hope it's okay to work in radians, and you know the how angles are measured in radians. So you can write a complex number in terms of the modulus of the complex number, which is L, and what is often called the argument of the complex number, or in engineering terms, we sometimes call this the face of the complex number, or the angle of the complex number, which is theta. This angle that it makes with the x-axis measured in anti-clockwise sense starting from 0. That's important. Okay, and that's called the face or the argument. Sometimes it's called the arg of the complex number. I'm not going to go into terminology issues between different math books and engineering books. Let me just call this the face angle. Okay, the face of the complex number, because that's what we would use in a Fourier series. All right, now this is important because you can interpret various operations on complex numbers as in terms of this argument and in terms of this face. Okay, so as an example, let's take two complex numbers. Let's take a complex number x1, y1. Okay, and it has an angle r and a phase theta. Okay, and let's take another complex number x2, y2. Oh, let's call this r1 and theta 1. And let's call this r2, x2, y2 as r2. And let's call this angle theta 2. Now, what if I multiply? Let's call this Z1, let's call this Z2. What if I multiply Z1 and Z2? Well, multiplication of Z1 and Z2 will give me a new complex number, whose length is going to be R1 times R2, okay, and whose angle is actually going to be theta 1 plus theta 2. If I multiply two complex numbers, then I have this new complex number whose angle is going to be theta 1 plus theta 2, and whose modulus is going to be R1 times R2. Okay. Now, this is one very, very important to understand. So Z1 times Z2 is a complex number where the modulus of Z1, Z2 is L1 times L2, or I call them R, so I'm going to use R1 times R2, and the phase of Z1 times Z2 is theta 1 plus theta 2. Now comes a very, very useful theorem that comes to us from mathematicians like Euler and De Moivre, and it's called De Moivre's theorem. And De Moivre's theorem says the following. So first of all, remember the number e to the x is basically going to be 1 plus x squared by 2 factorial. I hope you've done enough calculus to know what e to the x means. Now you can take this x and you can make this a complex number, okay? And in particular, you can do the following. E to the power j, let me just call it theta, is written as the complex number cos theta plus sine theta times j. Okay, and this is very, very important. This is, you can take the complex number j times theta in radians, and you can say e to the power j theta is just cos theta plus sine theta times j. All right, this is super important because what it allows you to do is, if you have a complex number with modulus r and with phase theta, then you can write z equals r e to the j theta, or which is r cosine theta plus sine theta j. And if you know trigonometry, this, you can actually verify this, because this is r, this is theta, and remember, this is y, and this is x. Now, if this is r, then x equals r cosine theta and y equals r sine theta, because sine theta, remember, is just this y divided by r. So this is another way of saying sine theta is y by r, cos theta is x by r. And you can see that you can write x equals r cosine theta, y equals r sine theta. So you can write z, the complex number you're interested in, as x plus yj, where x is this, y is this, or you can write it like this, okay, r e to the j theta. And this equivalence is called De Moivre's theorem. I apologize if I got the name of the theorem wrong. It's been almost 20 years since I first encountered these concepts myself, and I've just internalized them so much that I sometimes forget the names of these theorems. It's been quite a while since I learned the proof of these theorems themselves, which involves calculus. Okay, won't go into the proof right now, but this is super important, and this explains the reason why, if you have two complex numbers r1 theta 1 and another complex number r2 theta 2, then let's call this z1 z2. Now z1 is the complex number r1 e to the power j theta 1, z2 is the complex number r2 e to the power j theta 2. So z1 times z2 is the complex number r1 r2 e to the power j theta 1 e to the power j theta 2. So this is the complex number with modulus r1 times r2 and angle theta 1 plus theta 2. I hope this is okay. Okay, so multiplication of two complex numbers multiplies their modulus and adds their angles. Okay, so this is going to be important. So as a last topic, I will review the concept of complex, this is going to be super important, roots of unity. And then in the next lecture, I'm going to talk more about complex roots of unity and talk about Fourier transforms or discrete Fourier transforms using complex roots of unity. So what's complex root of unity? So a number omega, let's call these complex numbers omega, is a complex root of unity if omega power n is 1. So omega is said to be an nth root of unity if omega power n is 1. So what is 1? 1 is the special complex number which has no imaginary part and real part is 1. So which is modulus 1 times e to the power 0j. So the angle is 0, theta is 0. You can also say theta is 2 pi, 4 pi, and so on, but we will just say 0. Okay, and the modulus is 1. So 1 is a very special complex number, and omega is a complex number where we say omega to the power n, omega to the power n is 1. So let's call this angle theta, and let's call the modulus of omega r. So let's say omega equals r e to the j theta. Now what we want is r to the power n e to the power j times n theta. This is omega to the power n is 1. So if you compare the equations, then r to the power n is 1, and r is a real number, it's just a radius, so r must be 1. So the radius of this omega, the modulus of this omega must be 1, and e to the power j n theta must be equal to e to the power j, and this is 2 pi. Okay, so you take this as 0 or 2 pi, just serve your purposes. Like this is going to be a little bit self-serving. Therefore, omega is e to the power 1 times e to the power 2 pi divided by n j. So this angle is going to be 2 pi divided by n. And that is one of the roots of unity. We call this omega n. Okay. And likewise, it turns out that omega n to the power 2 is yet another root of unity. So omega n squared is e to the power 2 pi over n times 2j, okay, j being square root of minus 1, remember? And this is another root of unity. Likewise, omega n cube is another root of unity, omega n 4, all the way to omega n to the power n minus 1. And so the roots of unity can be seen as these vectors of length 1, and where the angle between each of these vectors is 2 pi divided by n. So if n, for example, is 10, then this angle is 2 pi divided by n, which would actually be 36 degrees. If n equals 10, these would be 36 degrees with each other. If n equals 20, they would be 18 degrees. If n equals 5, they would be 360 by 5, which is going to be what? 72 degrees. So depending on n, you have these vectors, n vectors, and these are going to be the roots of unity. Okay, so let's go back to the following problem. We wanted to see what are the third roots of unity. So remember, the three roots of unity are going to be like this. So you're going to have one of the roots, which is going to be the vector 1. The second root is going to have a 120 degrees. So this is going to be 2 pi by 3, which is 120 degrees. This is radians, this is degrees. And then the third vector is going to be 4 pi by 3, and that's 240 degrees, like that. So those are going to be, and these are all going to be 2 pi by 3, which is 120. And then last one is 2 pi by 3, which is 120. So you have three roots of unity, okay? Omega 1, omega n squared, and omega n cubed, which is actually going to get back to 1. So those are the three roots of unity. Okay, these are the three cube roots of unity. So what is this root? So omega n is cosine. So let's answer the question we left earlier, plus sine 2 pi over 3 j. You can actually calculate this. Cosine 120 if I'm not mistaken, is going to be what? Uh, so it's going to be minus cosine 60. Okay, so you can say this is minus square root 1 minus 1 by 2 plus square root 3 over 2j. If I'm not mistaken, check. And then the other omega n squared will become minus 1 by 2 minus square root of 3 over 2j. I might have exchanged these, just check. Okay, so these are going to be the three cube roots of unity. So these are the three cube roots, complex cube roots of unity. One of the roots is going to be real, which is just the root 1. The other two roots are complex roots. Okay, and this is going to be a very powerful way of looking at complex numbers. So let's look at one more example. Let's look at the 8th roots of unity. So remember, there are going to be 8 of them. And actually, they are quite interesting because the angles they make will be 2 pi by 8, which is 360 by 8, which is 45 degrees. Okay, so you're going to have one root, omega, and this root is actually going to be 1 by square root of 2 plus 1 by square root of 2j. And that's going to make a 45-degree angle here. The second root is actually going to be make another 45-degree angle, just j itself. Another root is going to be minus 1 by square root of 2 plus 1 by square root of 2j. The fourth root is minus 1. The fifth root is minus 1 by square root of 2 minus 1 by square root of 2j. This is the fifth root. The sixth root is just minus j. The seventh root is 1 by square root 2 minus 1 by square root 2j. And the last one is just 1 itself because 1 to the 8. So each of these are the 8 roots of unity that satisfy the equation x to the power 8 equals 1. So these roots of unity are going to be very, very important. So in the next lecture, I'm going to look at some of the properties of these roots of unity and get on to the description of what a Fourier transform is. So we are going to come up with two descriptions of Fourier transform, one in terms of a polynomial, another in terms of roots of unity. So I will see you in the next lecture. Bye then. All right, so welcome to the second part of the FFT lecture. And in the last part, we did a quick overview of complex numbers and we defined the roots of unity, the complex roots of unity. And these are solutions to this equation, x to the power n equals 1. Okay, and we saw that the roots of unity are n in number. Okay, and on the complex plane, if this is the real part and this is the imaginary part, then the roots of unity form these vectors, and each of the roots forms an angle of 2 pi, which is 360 degrees, 2 pi radians, divided by n, and each root has modulus 1. So this is omega n, which is called the first root, and this has a very special meaning. We'll talk about that in a second. The length of these vectors are all 1, and each vector forms an angle 2 pi by n over the previous vector, and you get n roots of unity. And remember, 1 is always a root of unity. So one of the roots is always 1, which makes an angle, depending on how you want to interpret it, it makes an angle of 2 pi or 0 or 4 pi, whatever you want to interpret it as. Okay, with the axis, then the other roots of unity make angles 2 pi by n. This makes an angle twice 2 pi by n. And then you have the jth root of unity makes an angle 2 pi by n times, not j, let's use k. J is square root of minus 1. Remember, 2 pi by n times k. Okay, and remember, a complex number can be written as z equals its modulus e to the power square root of minus 1 theta. This is square root of minus 1. And remember, theta is the angle it makes with the real axis, and r is the modulus of the complex number, which is the real valued length of this vector. I hope all of these are clear. Okay, now, so what we will do today is we will look at the nth root of unity. So for example, for n equals 8, we have 8 roots of unity. We saw that in the last lecture already. So the generator root, or the first root, makes an angle 2 pi by 8, which is 45 degrees. And this is actually 1 by square root 2 plus 1 by square root 2j. That's one of the first roots of unity. Let's call it omega 8. The second root of unity is omega 8 squared, which is actually, if you do the math, it actually comes out to j. So this is 0 plus 1j. The third root of unity is this. So these make 45-degree angle, or pi by 8. Sorry, 2 pi by 8. Okay, this makes 2 pi by 8, another 45-degree angle. This is just minus 1 by square root 2 plus 1 by square root 2j. The fourth root of unity is minus 1. Fifth root of unity is minus 1 by square root 2 minus 1 by square root 2j. Sixth root of unity is minus j. Seventh root of unity is 1 by square root 2 minus 1 by square root 2j. And the last root of unity is 1. Itself is a root of unity. Now, the roots of unity are generated by a single generator. And let's call this, in this case, it's omega 8. In the general case, it will be omega n, which is just cosine 2 pi by n plus sine 2 pi by n j. That's the complex number. It's e to the power 2 pi by n times j, which is just the complex number that makes an angle of 2 pi by n with the real axis. And this is this complex number, and we call this omega n. Its modulus is 1. Now, all the roots of unity are omega n to the power 0, which is 1, omega n to the power 1, which is omega n itself, omega n squared is also a root of unity, all the way to omega n to the power n minus 1. So these are all the roots of unity. So these are the n roots of unity, and they are all generated as powers of the generator root, and then you square that power, or you take the generator root and you take the cube of it. So the roots of unity are all obtained, and one is a very special root, which is the 0th power of the generator, and this is the generator itself. Okay, so all the roots of unity can be viewed as powers of this generator root. Okay, which is this special root which makes the smallest angle 2 pi divided by n, not 0, smallest non-zero angle 2 pi divided by n with the omega n with the real axis. Okay, and this is kind of an important thing to remember, that the roots of unity are all generated by a single generator as powers of this generator. So the jth root of unity, therefore, or let me not use j because I'm already using j for square root minus 1, remember, so let's call it kth root of unity, is going to be e to the power 2 pi over n k j. So it makes an angle, some angle, which is going to be 2 pi over n times k, and its modulus is going to be 1. And this is actually omega n to the power j. Okay. Likewise, omega n to the power n is 1. Why is that? Because omega n is e to the power 2 pi over n j. Omega n to the power n is e to the power 2 pi over n times n j. That's just e to the power 2 pi j, which you can, at the end of the day, is cos 2 pi plus sine 2 pi j. This is just 0. This is just 1. So the whole thing is 1. So omega n to the power n is 1. This is important. Okay. So what are the different powers of omega n then? So if you take omega n to the, if you take omega n, if you take omega n squared, that rotates by 2 pi by n. If you take omega n cube, that rotates by 2 pi by n. If you take omega n4, that rotates by 2 pi by n. So each omega n to the power j is j rotations by 2 pi by n in anti-clockwise sense. And then when you make n such rotations, you come back to the vector 1. Okay, so this is going to be important. So omega n, the generator, is a vector such that omega n to the power 0, omega n to the power 1, omega n to the power n minus 1. And then, so it takes n moves to make one complete cycle. So it's going to be a vector, suppose starting at 1, if I do omega n to the 1, omega n to the power 2, omega n to the power 3. So it takes n rotations and comes back to 1. And then if I keep rotating it, it's going to cycle forever. So that's omega n. Let's look at a different vector. Let's look at the vector. Suppose n is even. Let's look at the vector omega n squared. So then something very strange happens, right? Omega n squared is a vector that makes 2 pi by n times 2 radians. Okay. Now this vector is going to rotate at twice the rate, or more generally, it's going to take in half the time it will go to 1. So omega n2, let's call this z. Then I get z to the 0, z to the 1. And then if I go to z to the power n by 2, I come back to 1. So this actually is a vector that's rotating twice as fast as omega n, okay, because it comes over in half the time. Likewise, suppose n is divisible by 3. Let's assume n is divisible by 3. Then omega n to the power 3 is going to rotate and come all the way back in n by 3 steps. Okay. Likewise, omega n to the power k completes one full rotation in n by k steps, assuming that k divides n. Okay. So suppose k is even. Let's look at a special root. Let's look at omega n to the power n by 2. So what is omega n to the power n by 2? It's the middle root of unity. So you have omega n to the power 0, omega n to the power 1, omega n to the power n minus 1. So the one in the middle is omega n to the power n by 2. That's right at half. Now what is this root? So some math, it's e to the power 2 pi over n j times n by 2. This is omega n. This is to the power n by 2. And this is just e to the power pi j. And this is famous Euler's formula. This is minus 1. So the middle root, if n is even, and if n is odd, this root is not going to exist because n by 2 doesn't exist if n is odd. Okay, makes sense, hopefully. So this is just the number minus 1. And if I rotate this root, omega n to the power n by 2, the whole squared, that just becomes this root plus 1. And then omega n to the power n by 2, the whole cube, comes back to minus 1. So as you can see, what happens is it basically keeps rotating back and forth. Okay. And its frequency is just 2. In every 2 steps, it comes back to itself. It goes to minus 1, plus 1, minus 1, plus 1, and so on. So in every 2 steps, it repeats itself. Okay. So this frequency is 2. So this is going to be, so each root of unity has a frequency. Okay. Each root of unity has a frequency, which is how many rotations it takes before it comes back to the cycles back to the original root, which is 0. Okay, I hope this is fine. Now, what this provides us is a way to interpret sequences. So now, if all of these ideas are okay, let me explain what is the Fourier transform, or more technically, it's called the discrete Fourier transform of a signal. And for our purposes, a signal is just A0, A1, A2 to an minus 1. So it's just n real numbers, some real numbers. I don't care what numbers. These are just some numbers that, and we interpret this as data. So at time 0, I have A0. At time 1, I have A1. At time 2, I have A2. At time 3, I have A3, and so on until I go to time n minus 1. And there's an unspoken assumption that if I want to move beyond time n minus 1, it just repeats. It's just periodic and repeats infinitely. Though this is never, you don't need this assumption. This is just important because it drives the math. Okay, so now what is a Fourier series then? So the way to interpret a Fourier series is like this. So think of the polynomial a of x as this: a0 plus a1x plus a2x squared all the way to a n minus 1 x to the power n minus 1. This is a polynomial of degree n minus 1. Okay, and this is just taking these and making it into a polynomial. Example, suppose my sequence is plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. That's my sequence. My polynomial in this case is 1 minus x plus x squared minus x cubed plus x4 minus x5. So I just make these the coefficients of my polynomial. Now x is a variable. I don't know what x is, but I'm going to evaluate this polynomial for different values of x. So different values of x. So what is the Fourier series then? The Fourier transform is simply going to be, let me take this polynomial, and let me evaluate this polynomial for various roots of unity. So remember, evaluate this polynomial for various roots of unity. Specifically what? So specifically, I'm going to do a of omega n to the power 0, a of omega n to the power 1, a of omega n squared, all the way to a of omega n to the power n minus 1. I'm mixing up small n and capital N. These should all be capital N, capital N, capital N, capital N, capital N. Now, if I evaluate these polynomials, remember, omega n to the power 0 is just 1. So this is just going to give me a0 plus a1 plus a2 plus a n minus 1. This is just going to be the sum. This is going to give me a0 plus a1 omega n plus a2 omega n squared plus a n minus 1 omega n to the power n minus 1. So these are all going to give me different complex numbers. And let me write these complex numbers as a capital A0, capital A1, capital A2, and capital A n minus 1. And this is what we define as the discrete Fourier transform of my sequence. Okay, now you may wonder, why did I define it this way? What are the properties? We will talk about all of that in a second. But this is the definition, and you have to just accept this definition. Let's look at the properties in a bit, but this is the definition. Let me give you an example. So let's take a small example. Let's take the sequence plus 1, minus 1, plus 1, minus 1. This is a sequence of 4 numbers. So my n, I've been using capital N and small n. So let's just say it's 4. Whatever I use, it's 4. And small n, capital N. My roots of unity, fourth roots of unity are omega 4 to the 0. So omega 4, you can verify, is just j. It's just j. Okay. And then you have j squared, j cubed, and j to the 4 is just 1. So this is j to the 0, if you will, j to the 1. So those are my 4 roots of unity. Okay. So my roots of unity are omega 4 to the 0, which is just 1, omega 4 to the 1, which is just omega 4. In this case, it just happens to be the square root of minus 1, which is j, omega 4 squared. I'll just do everything in white, which is minus 1, omega 4 cubed, which is minus j. So my Fourier series is going to be a sub 0. So, and remember, the polynomial associated with this is a of x is 1 minus x plus x squared minus x cubed. Okay. A sub 0 is just going to be 1 plus minus 1 plus 1 plus minus 1, which is 0. The first coefficient, a sub 1, is just going to be 1 plus minus 1 times j plus 1 times minus 1 plus minus 1 times minus j. So a sub 1 in this case is going to be 1 and then minus 1 cancel, minus j and j cancel is 0. Okay. The second one, a sub 2, is going to be plus 1 minus 1 times j squared plus plus 1 times j cube plus minus 1 times j, sorry, I'm off by 1, apologies. So j squared, j cube, j4. All right, so this is going to be what? So this is going to be 1 plus minus 1 times minus 1, which is 1 plus 1 times j cube. I think I made a mess. Let me do it again. So remember, A2 is A evaluated on the polynomial j squared, which is just A evaluated in minus 1. And that's going to be simply this sequence plus 1 plus minus 1 times minus 1 plus, this is third sequence, plus 1 times minus 1 squared plus plus 1 times minus 1 cube. Sorry, minus 1. This is just A0, A1, A2, A3. Okay. When the dust settles, you can check this is actually 4. And likewise, A3 is just A evaluated on J cube. And when the dust settles, you can check this is actually 0. So the Fourier series of plus 1, minus 1, plus 1, minus 1, the Fourier transform, this discrete Fourier transform is just the sequence 0, 0, 4, 0, right? We'll interpret this in a second. This has a nice interpretation, but this is the discrete Fourier transform. All right. So to recap, what is the discrete Fourier transform? So the discrete Fourier transform is if you have a sequence A0, A1 through A sub n minus 1, okay? I'm using capital N and small n interchangeably here. Forgive me for that. So then you define the polynomial A of x is A0 plus A1x plus A n minus 1 x to the n minus 1. And then you have the sequence A0, A1 through capital A n minus 1 is going to be the discrete Fourier transform where A sub j, or let me not use the term j because j is already used from square root of minus 1. Let's call it A sub k is just the polynomial A on omega n to the power k. Okay, it's just the polynomial A evaluated at the kth root of unity. So that's just A0 plus A1 omega n to the k plus A2 omega n to the power k the whole squared plus A n minus 1 omega n to the power k the whole to the power n minus 1, which is some complex number. And that's the kth Fourier coefficient. And that way you define all the Fourier coefficients, capital A0 to capital N minus 1. And this operation is called the discrete Fourier transform. So what does it mean to compute the discrete Fourier transform? Very simply, you take the original sequence, you imagine this polynomial, and you evaluate this polynomial on all these endpoints. The endpoints you're evaluating this polynomial are the n roots of unity. So to repeat, evaluate the polynomial on each root of unity, and you would get this sequence. You would get this sequence. Now, the interesting thing is this. The interesting thing is that if you have this discrete Fourier transform, you can actually define its inverse. So if you have A0 to An minus 1, there is a symmetric process of inverting it called the inverse Fourier transform, which is simply going to give you back the original numbers. Now, how do I interpret this inverse Fourier transform? Very simple. I'm going to create a new polynomial. Let's call this capital A of x. Okay. And for technical reasons, I have to divide by n. It's 1 divided by n, A0 x to the power 0 plus A1 x to the power 1. Let me actually use the term z because we're going to have complex numbers, right? Z to the 0, A1 z to the 1 plus an z to the power n. Okay, so this is going to be my A of x. And what I do is I'm going to say AI, the ith coefficient here, is just A evaluated on omega n conjugate to the power I. Remember, the conjugate of a complex number is A minus bj. So therefore, if you take omega n, its conjugate is this, okay, omega n bar. Okay, so I just take the conjugate complex number and I evaluate the conjugate complex number to the power I, evaluate this polynomial, and I have to, for technical reasons, divide by n. Okay, so that gives me what I need. Oh, okay. I think I made a mistake. The conjugate, this diagram is misleading. So the conjugate complex number is like this. The conjugate complex number is actually this one. Remember, conjugate of a plus b is a plus minus b. So if this is a comma b, this is a comma minus b. I hope that makes sense. The conjugate reflects around the real axis, not the imaginary axis. Sorry for the confusion. So what does it mean then? Yeah, if I take the discrete Fourier transform a0 to a n minus 1, then I can recover the original sequence back by just taking a very similar process to the original Fourier transform, except I have to divide stuff by 1 by n. And there is a reason I have to do that. I can explain why we need to do that later, but just take my word for it that we need to divide by 1 by n. Okay, and that's the only difference. And then you take this a0, consider the polynomial. This should be a of z. Sorry about that. A of z is a0 z to the power 0 plus a1, which is the first coefficient, times z to the 1, a n z to the n. And you can recover back a sub I by evaluating this polynomial at omega n conjugate to the power I. Just like capital A sub I was the original polynomial at omega n to the power I evaluated at this point, this is the polynomial evaluated at this point. Okay, the conjugate. Now, what's the conjugate generator? So if this is the original generator, okay, and the powers of this generator are going to be omega n squared, omega n cubed. They are rotating in the clockwise and the anti-clockwise direction. The conjugate turns out to be this one. So this is just omega n conjugate, and then omega n conjugate squared just rotates in the anti-clockwise direction. So think of the powers of the conjugate. So omega n conjugate to the power j is just going to be j rotations in the clockwise direction, just like the original one was in the anti-clockwise direction. But this gives us an interesting interpretation of the Fourier coefficient. So this gives us an interpretation of the Fourier coefficient. What is this interpretation? The interpretation is like this. Let's take these Fourier coefficients a0, a1 to a sub n minus 1. Let's take these n minus 1 Fourier coefficients. Let's do a favor and let's already do the division by n here. Let's just divide each of these coefficients by n already, just to avoid this confusion. All right. Now think of a sub I, the ith element in the sequence. So a0, a1, a2. So each of the sequence is this, right? a0, a1, a2, a sub I, and so on. So you can write a sub I as a0 omega n conjugate to the power I to the power 0 plus a1 omega n conjugate to the power I to the power 1 plus a2 omega n conjugate to the power I to the power 2 plus a sub n omega n conjugate to the power I to the power n minus 1. This is n minus 1. All right. So this is how you write it. Now imagine each of these vectors. So imagine omega n conjugate to the power I to the power 0, omega n conjugate to the power I to the power 1, so on. Now it turns out that each of these vectors are going to rotate around are going to rotate at some specific frequency. So this particular vector is just 1. It never rotates, it just stays where we are. So you can say it rotates at 0 frequency. This vector, omega n conjugate to the power n to the I to the power 1, is just this. So it's just take the generator omega n conjugate and rotate it I times already. And this is omega n conjugate to the power I. And then this vector takes, suppose n is I is divisible by n. So n by n cycles Okay, it's actually going to rotate in the clockwise direction. It comes back to 1. So this is a vector that rotates at n by I frequency. Okay, likewise, omega n conjugate I, the whole squared, is a vector that rotates at n by I, sorry, uh, n by 2I frequency. Okay, likewise, omega n I conjugate to the power k rotates at n by ki frequency. All right. So what you're saying is that a sub I is written as some combination a0 of a vector that rotates at this frequency, uh, a1 of a vector that rotates at frequency n by I, a2 of a vector that rotates at frequency n by 2I, and so on. So if you want to think about this, think about each Fourier coefficient being associated with a vector. So this first Fourier coefficient is associated with a vector that is just 1, that never rotates. This Fourier coefficient is associated with the generator omega n conjugate that takes n rotations to come back. So this is taking n rotations to come back. This vector will take n by 2 rotations to come back. This vector is actually going to be the other way around. This is going to be omega n conjugate to the power n minus 1, which you can prove is actually omega n, strangely enough. So this is a vector that actually will rotate in the opposite direction and take n rotations to come back. So what we have is we associate each of these with a vector that's cycling around and coming back with a different frequency. And you're saying that a sub I can be written as a combination of these coefficients times these vectors. And that's a way of thinking of these vectors, these a sub i's, as being associated with the frequency components of your original signal. Okay. Now, this is going to be it's a little hard to visualize and you need to spend some time with it. So I suggest looking at some nice visualizations on the web. For example, the 3 blue, 1 brown. I'll place a link right here. They have a very beautiful visualization of this, though they are looking at a slightly different version called the continuous Fourier transform. The same thing holds for us. We just use something called the discrete Fourier transform. So our vectors are not moving, the clock is not moving continuous, the clock is ticking discretely 1 second at a time. It's not just like rotating or winding continuously. But if you understood that, it's basically the same idea. Okay, so now comes the interesting part, which is let's recap and talk about what is the Fourier transform, what's the inverse. So Fourier transform of a series a0, a1 through a sub n minus 1. Imagine the polynomial a of x, just to recap. Imagine the polynomial a of x, which is a0 plus a1x plus a n minus 1, x to the n minus 1. This is just x to the 0, which is 1. And then evaluate this polynomial at omega n to the 0, omega n to the 1, omega n to the n minus 1. Okay, and this gives us the various Fourier coefficients. And likewise, the inverse, so this is called the Fourier transform, or the Fourier transform of the sequence, or the discrete Fourier transform. If you want to be very specific, this is called the discrete Fourier transform. Okay, and now what happens is once you have the discrete Fourier transform, you can imagine the reverse process, which is imagine this polynomial. Okay, and then put a 1 by n here. Okay, you have to divide by n. Okay, that's important. And now you have a0 is the capital A polynomial on omega n conjugate to the power 0. A1 is the capital N polynomial on omega n conjugate to the power 1. A sub I is the capital A polynomial on omega n conjugate to the power I. And A sub n is this polynomial on omega n conjugate to the power n minus 1, n minus 1. Okay. Remember, we take a sub n is the same as a sub 0, and remember we assume the series continues. Okay, so this is the interpretation, and this is called the inverse Fourier transform. Now, is it obvious that you get back exactly the same sequence as you started? Is this obvious? Not really, but we can prove this. So it's actually a very nice exercise in mathematical proof to show that the inverse Fourier transform applied to the, will actually give you back the original sequence. So you can actually prove this. It's just a bit of manipulations, algebraic manipulation, knowing a few useful facts about the roots of unity, and a bit of simplification, geometric series, you get back. Okay, it's not a difficult proof, but I'm going to skip the proof here. Okay, now what does it take to calculate the Fourier transform then? So to calculate the Fourier transform, suppose I'm given a sequence, and suppose I can manipulate complex numbers, in which you can, then I simply have to evaluate this polynomial a of x at n different points, and which is a of omega n to the power 0, a of omega n to the power n minus 1. So I have to evaluate a at n different points. And each evaluation is just summation. So it's you have to do a0 plus a1 times x plus a2 times x squared plus an times x to the power n minus 1. So each evaluation takes theta n multiplications and additions. And so you have to do n such evaluation. So naively, computing the Fourier transform takes theta n squared time, naively, if you just follow the definition. And likewise, the inverse Fourier transform also takes theta n squared time, because you're doing what? You're doing calculating this polynomial and evaluating this polynomial at n different points, which is just omega n conjugate to the power 0, omega n conjugate to the power n minus 1. So you're just evaluating this polynomial back and then dividing by, yeah, so you have to, this is 1 by n. Okay, so you just take this polynomial, evaluate it at n points. So again, it's theta n squared. Now in the next lecture, we are going to use divide and conquer to show that instead of theta n squared, you can do it in theta n log n. So I will see you there. Thank you. Okay, so now we are going to be talking about the algorithm that we know as fast Fourier transforms. Okay, and basically what it is a way to calculate the discrete Fourier transform of a sequence a0 to a sub n minus 1. And recall what it means. Imagine the polynomial a sub x is a0 x to the power 0 plus all the way to a sub n minus 1 x to the power n minus 1. And the idea is evaluate a at various roots of unity. And this gives me a series of complex numbers, okay, where the ith number is the polynomial a evaluated at the ith root of unity. Okay, and this is the result of the discrete Fourier transform. Last time we saw that naively calculating the polynomial at n different points requires theta n squared operations. And operations are additions and multiplications of complex numbers. And to add or multiply a complex number, remember it costs about twice as much or 4 times as much. So constant number of floating point additions or multiplications. All right, so this was the naive approach. And today we are going to look at a very surprisingly efficient approach called fast Fourier transforms that's based on divide and conquer. And the basic idea is as follows. So suppose I want to look at this a of x, this polynomial that I want to evaluate. So it's a0 plus a1x plus a2x squared all the way to a, let's assume n is even, okay, a n by 2, x to the power n by 2, all the way to a n minus 1, x to the power n minus 1. So we have this, all right? Now let me decompose this polynomial into two parts. Like in divide and conquer, I have to first divide, So I'm going to divide this polynomial into two polynomials, and I'm going to call them a even plus a odd of x. Okay, so let me do it as follows. So the way I'm going to do it is slightly different from this. So let me take all the even coefficients. So let me take a sub 0, and let's assume that n, which is this degree minus 1, is even. So n is even, and n is divisible by 2. So let's take a sub 0 plus a sub 2 x squared plus a sub 4 x to the power 4 all the way to a sub n minus 2 x to the power n minus 2, plus let's take the odd coefficients 1, 3, and so on. Okay, this is going to be a sub 1 x plus a sub 3 x cubed. So these are going to be even parts of the polynomial, and this is going to be the odd coefficients of the polynomial. So I'm going to divide it into two parts this way, and this I'm going to write as a sub 0 plus a sub 2 x squared all the way to a sub n minus 2 x to the n minus 2 plus x times a sub 1 plus a sub 3 x squared plus a sub n minus 2, sorry, a sub n minus 1 in this case, x to the power n minus 1. So I'm just writing, taking this x out in common here, x out in common, all right? And this, let me call this a odd, but not as a function of x. Let me call it as a function of x squared. And then this is x times, actually, this should be a even because these are even numbers, a even. And then I'm going to call it x times a odd x squared as a function of x squared, not as a function of x. Because remember, I'm just plugging in x squared, this a 4x to the 4. So what is a even of z? So that's just the polynomial a0 plus a2z all the way to a n minus 2 z to the power n minus 2 over 2. Okay, what is a odd? That's just a1 plus a3z. I'm just changing this variable called z. And remember, you're plugging z equals x squared. All right, a sub n minus 1 z to the power n minus 2 over 2. Okay, so these are the two polynomials, a even and a odd. And to calculate each of these Fourier coefficients, remember, to calculate the Fourier coefficient a sub I need to calculate the a even polynomial of omega n to the power I, the whole squared, plus the odd polynomial, so omega n to the power I times the odd polynomial a odd omega n to the power I, the whole square. Okay, now comes a very interesting observation. So let me write this interesting observation. If n is even, let's say if n is even, and of course n greater than 2 greater than equal to 2, that's important, then look at this omega n to the power I, the whole squared. This is just e to the power 2 pi I over n j, okay, j being square root of minus 1, okay, the whole squared. This is just, you can write it in a different way. You can write it as 2 pi I, this to the power 2 now becomes 2 times here, okay, times j. So this just becomes multiplication. This, you can write it as e to the power 2 pi I divided by n over 2j. So bring this 2 down here, and you have n over 2. Now this is nothing but omega of n over 2 to the power j. Okay, sorry, to the power I. I'm having difficulty with my coefficients today, to the power I. So this is an important fact. Omega n to the power I, the whole squared, is this 2 comes down here and divides this n, so it becomes omega n over 2 to the power I. This is important. Therefore, if I go here, then each of these, I can write it as omega n over 2 to the power I. and this is just omega n over 2 to the power I. So therefore, the ith Fourier coefficient is a odd, uh, sorry, let me write it starting from even, then write the odd term, excuse me. So it's a even omega n over 2 to the power I plus omega, watch this, omega n to the power I, a odd omega n over 2 to the power I. This is going to be important. Let's keep this in mind for a second, and I'm going to interpret this. So how am I going to interpret this? So what have I done so far? I have started with a sequence, and then I have split it into two sequences, A0, A2, an minus 2, and this is the A even sequence. Okay, and then I've split it as A1, A3, an minus 1, and this is when n is even. If n is odd, I cannot do this. I have to do something else, which we won't do right now. We'll just assume n is even. So I assume this is a even, a odd. Now, if you view this as a polynomial, you get a even of z. And if you view this as a polynomial, you get a odd of z. But remember, these are sequences of length n over 2, not n. So these are sequences of length n over 2, n over 2. Now, the Fourier transform, look at the Fourier transform of this sequence. Fourier transform of this sequence is going to be a even, it's going to give you some numbers, a even 0, a even n minus 2. Okay. So you're going to get some numbers here, and you're going to get some numbers here if you did a odd 1, sorry, 0, a odd n minus 2 over 2. All right. So these are going to be the Fourier transform of these individual sequences, the odd coefficient, the even coefficients, and the odd coefficients. Now, the interesting thing is this. A or even, for the even Fourier transform, A even I is just the polynomial A even on omega n over 2 to the power I. So this is actually why omega n over 2, because it's a n over 2 length sequence. So I have to look at the n over 2th root of unity. Likewise, the ith coefficient here is going to be a odd I, which is a odd, the odd polynomial, evaluated at omega n over 2 to the power I. So let's interpret this. So this says the ith Fourier coefficient of a0 to an minus 1, the original sequence. So the ith Fourier coefficient of the original sequence is the ith Fourier coefficient of the even sequences, okay, with half the number, plus omega n to the power I, the ith Fourier sequence of the odd sequences. So if I can compute the even Fourier sequence and the odd Fourier sequence, then I can combine them using this equation to compute the original Fourier sequence. Let me repeat this. This is super important. If I can compute the even Fourier sequences and the odd Fourier sequences, then I can just combine them to get the original Fourier sequence. So how does that go? That goes like this. I take my original array, I take the odd even coefficients. There are n by 2 of these. There are n in the original. I have to assume n is an even number. Okay. And then I take the odd coefficients. Again, there are n by 2 of these. And then I'm going to compute my even Fourier coefficients recursively. You can see we are beginning to form a divide and conquer algorithm here. So I'm going to get n by 2 even coefficients, and I'm going to get n by 2 odd Fourier coefficients. Okay, it goes from 0 to n by 2 minus 1, 0 to n by 2 minus 1, so n by 2 of these. And then The jth Fourier coefficient, or I shouldn't call j, the kth Fourier coefficient in the original one is just a even k plus omega n to the power k, a odd k. So that's going to be the kth Fourier coefficient. Now you may ask, what happens if k is more than n by 2? Well, if k, this is if k less than n by 2. If k is more than n by 2, it's just a even k minus n over 2, all right, plus omega n to the power k, a odd k minus n over 2. Or okay, so I hope this is clear. And what this does is it gives me a way to reconstruct the original sequence a0 to a n minus 1 given the Fourier coefficients for the odd and the even parts. Okay, so to recap, I have my original sequence of n must be divisible by 2. Okay, and that's a0 to a n minus 1, a sub n minus 1. I take the even coefficients, even indices, the odd indices. This is a different way we are used to. This is a0, a2, a n minus 2. This is a1, a3, a5, a n minus 1. And then I compute the fast Fourier transform of this. I compute the fast Fourier transform of this. I get my odd sequence, even sequence Fourier transform. I get my odd sequence Fourier transform and just combine, and I get my Fourier transform for my original set of sequence. So this is how I'm going to compute Fourier transform. Now the base case, so remember, if I have a Fourier transform of n, then I'm computing two Fourier transforms of size n over 2. And if I keep recursing, the base case is when you have to compute a Fourier transform of just a single sequence. So if my sequence is just a single number, a0, its Fourier transform is just itself. The Fourier transform of a single sequence is itself. And so that's quite easy. So my base case is when n equals 1, I stop. Now, one of the problems is we have just shown you how to divide things when n is even. What about when n is odd? It turns out to be a little bit more complicated when n is odd. So there is a more generic algorithm called FFTW. This is fast Fourier transform in the West, okay, by two very, very famous computer scientists, mathematicians, Cooley and Tuckey. Okay, so they have a very famous algorithm that can handle any n. We just assume that n is always even. So if you have a number that's always even when you keep dividing by 2 all the way to 1, so then n must be a power of 2. So we are doing the special case where n is a power of 2, but the more general case where n is not a power of 2, there are algorithms, except that they have to do divide and conquer differently if n is odd or n is even. The details are a little bit more involved, so I'm not going into it. But this is the basic idea for fast Fourier transform. What about the running time? Well, if you want to do a fast Fourier transform on n, then you do two fast Fourier transforms on size n over 2. And then the extra work of combining is just theta of n. So combination is just element-wise addition. So n element-wise additions. So of complex numbers, so that's just theta of n. And this is if n greater than 1. It's theta 1, otherwise if n equals 1. And so using the master method, this is A, this is B, this is C is 1. Okay, you get theta of, this is the same complexity as merge sort, interestingly enough. So this is just theta and log n. So you can calculate Fourier transform in theta and log n. Now, let me ask you a question then. What's the complexity of doing an inverse Fourier transform? Remember, inverse Fourier transform uses pretty much the same process as the forward Fourier transform, except that wherever we are using omega n, we would use omega n conjugate, and we would be dividing by n. So taking all of that into account, it's still the same algorithm with some modification, and it can be done also in theta and log n time. So this is going to be the overall idea behind Fourier transform and fast Fourier transforms. So let me now go through some code and actually show you how the calculation happens. All right, so time to look at some code. So for that, let me share my Jupyter notebook, which I have posted online. So hopefully you can see that. So this is the Jupyter notebook I've posted for you to be able to see. And here is some, I've shown you how to use complex mathematics in complex number manipulations in Python. So in Python, you have a package called CMath, where you can use complex numbers. And you can actually write down, there is a shorthand for writing a complex number. You can write a number as like, for example, 1.0 minus 2.1, and then write down a j immediately after the second number, and this becomes a complex number. Okay, for example, minus zero point 0.5 minus zero point 0.5j. So manipulating complex numbers in Python is quite easy. You can convert it to what is called polar coordinates, where you can get the modulus and the phase of the complex number and so on. Now, I've shown you a simple routine to get you the n roots of unity for various values of n. So you can see the various roots of unity. So the second roots of unity are +1 and -1. Note that there is floating point error. So this is actually 10 to the power minus 16. So this number is a really, really tiny number, which you might have to ignore. So sometimes you have numbers like 0.499999998, which is just zero point 0.5. And these are coming out because of floating point errors. So you have to be a bit careful manipulating complex numbers. So this is the naive computation of Fourier series or Fourier coefficients. So given a sequence of a zeros and to an, uh, what we do is we first calculate the generator of all the nth roots of unity, and we calculate each aj as a polynomial involving the sequence, where we are calculating it for w, which is wn to the power g. Okay, so you can look through this code and see that it's a naive n squared calculation. There are two loops that goes from 0 to n minus 1, 0 to n minus 1. So the overall procedure takes n squared time. All right. Now, this is the FFT algorithm that we discussed. So here I do a recursive implementation. I start with a sequence, and if the length of the sequence is 1, then the sequence itself is its own fast Fourier transform. Otherwise, I take the length of the sequence and I assume that the sequence must be even. So the sequence length must be even, power of 2, or else my algorithm doesn't work. Okay. Now, what I do first is I get the even elements and the odd elements of the sequence by taking the 2j indices and the 2j plus 1 indices for j ranging from 0 to n by 2 minus 1. Okay. I recursively call a fast Fourier transform on each of these sequences. Okay. And now I simply go through my coefficients, and then I compose the return fast Fourier transform, the original sequence, where I simply uh, add and subtract this number, which is wn to the power k. Okay, wn to the power k, and that gives me the kth coefficient. I also do it for the k plus n by 2th coefficient, which has to be like this. Okay, so this is a little bit of a trick that avoids the double calculation, and so this is how I compose the fast Fourier transform. And likewise, the inverse Fourier transform is exactly the same algorithm, except that I have to divide by 1 by n. But since n is a power of 2, uh, I just have to divide at each step by 1 by 2, and that takes care of it. The details are a little bit tedious, but I hope I will post this notebook, and I hope you have the time to go over it. So we can do various sequences. We can take their fast Fourier transform, and we can take their inverse Fourier transform and verify that we get back the same sequence. All right. So next lecture, I will talk more about how to do fast Fourier transforms and how to interpret fast Fourier transforms and how to use it for some interesting applications. See you there, and thank you so much. Hello, and welcome to this lecture where I'm going to explain a very interesting and important application of FFT, fast Fourier transform, for multiplying two polynomials. So what is polynomial multiplication? So you're given two polynomials. Let's call them a of x. Oops, sorry about that. Let's fix this. So you're given two polynomials, a of x. Let's say it's degree n minus 1, okay? And you're given another polynomial b of x. Let's also say for convenience, it's degree n minus 1. So these are both degree n minus 1. And I represent A as a sequence, A0 through A sub n minus 1, a sequence of n elements, and B as well as a sequence of n elements, like that. Okay. So these are two sequences of numbers. And I would like to find the product A of x times B of x. So how do we calculate this product? Well, this is very similar to multiplying numbers, and there is a naive algorithm which you can guess is going to run in theta n squared time. And how does that algorithm work? Well, something like this. Let's take an example. Let's take the polynomial 1 plus x minus x squared and 1 minus 2x squared. Okay. Now, if I want to multiply this, this is a of x, this is b of x. All right. Now, what do? I take 1 plus x minus x squared times 1 plus 0x times 1 plus x minus x squared minus 2x squared times 1 plus x minus x squared, and then simplify, and you get something like, uh, let's do this calculation. So you get 1 plus x, and this minus 3x squared, if I'm not mistaken, um, minus 2x to the power 3 minus 2x to the power 4. So in general, what you would do is you would take one of the polynomials, uh, and then you would take each coefficient of this other polynomial, multiply through, like you would do b0 times a0 plus a n minus 1, and then you would do b1 times, and then you would shift by 1 and you would say 0, a0 times a n minus 1 plus b2 times, and then you would put two zeros, okay? Um, and you would do all these, and then you would take the addition, and that would give you the final result. And remember that the final result is a list of size 2n. So A0 times B0, let's call the final result C. So then the final result will have 2n coefficients, C0 to C2n minus 1. Or uh, more important, it would be 2n minus 2. Minus 2, because it's n minus 1, n minus 1, the maximum degree would be 2n minus 2. All right, I hope this is okay. So this will give you this. And the naive algorithm is theta n squared. Today, I'm going to, in this lecture, talk about how to use FFT to solve this problem in theta n log n. And what's the idea? The idea is very simple. Suppose I have a of x, and I calculate its FFT coefficients, a0 through a sub n minus 1, and I have b of x, which is b0 to b sub n minus 1, then let's calculate the polynomial c of x, which is ax times bx. What are the FFT coefficients of c? Now, remember, FFT coefficients are obtained by evaluating A at various roots of unity. So the FFT coefficients are A0 is A on omega n to the 0. In general, A sub I is A on omega n to the I. A sub n minus 1 is the polynomial A on omega n to the n minus 1. Likewise for B, now, so if I wanted to multiply A times B, let's call this C, then C at omega n to the I is just A at omega n to the I times B at omega n to the I. So just the ith coefficient of the FFT. So To get the ith coefficient of the FFT of C, I just need to multiply the ith coefficient of the FFT of A and B, and I'm done. Except for one small catch. Even though A has n coefficients, B has n coefficients, you know that C is a polynomial of degree 2n minus 2, so it needs to have 2n minus 1 coefficients. So unfortunately, the number of coefficients for C doubles and it's different. So how do we fix this? So to fix this, we have a very simple trick. You can write A as A0 plus A1x all the way to an minus 1 x to the n minus 1 and pad it with a bunch of zeros. So 0x to the n plus 0 x to the power 2n minus 1. So pad it with a bunch of zeros. Similarly, pad B with a bunch of zeros. Okay, so pad it with a bunch of zeros. And now when I take the coefficients, the FFT coefficients, I would have 2n minus 1 FFT coefficients. Likewise, or 2n minus 2 here, A0 to A2n minus 2, that's 2n minus 1. And then I have B0 to B2n minus 2. And then I get C 0, which is A0 times B0, just directly multiply them. C2n minus 2 is A2n minus 2 times B2n minus 2. And even though I do not know the C polynomial, I know its FFT coefficients. And now I just do an inverse Fourier transform and out comes the coefficients for the C polynomial. That's it. It's extremely nifty. And the idea is I have my A, I have my B. I calculate FFT, so I pad it with a bunch of zeros. I pad it with a bunch of zeros. I calculate FFT. Even though this is 2n, roughly 2n, the algorithm is 2n log n, which is just n log n, n log n. Okay, because I put a theta in front of it, then factor of 2 doesn't matter. So I get the FFT sequence for A and B. I just add them. This is just theta n. Remember the 2 is just gets absorbed in the theta here. And then I get FFT coefficient. And then theta n log n. I do my inverse Fourier transform, which is just FFT. And then I get my C. So total complexity of polynomial multiplication is theta n log n, as opposed to the naive algorithm, which would have given you theta n squared. No naive algorithm. This is how you would do polynomial multiplication using FFT. This is kind of simple. I hope the ideas are clear, and we will explore these ideas a little bit further during the assignment that you have this week. Thank you so much, and I will see you in the next lecture. All right. So in this final part of FFT, we are going to talk briefly about how we can use FFT in some signal processing applications. Now, this is going to be really brief because often this is actually these kinds of things are actually covered in its own subject. So you will learn signal processing, but signal processing is its own subject and not part of algorithms per se. And some of the details of Fourier transforms, the math behind it, I haven't really explained any of that to you. So this is going to be a little bit at a high level. But let me anyway explain this. So suppose we look at a signal, and I will show you some examples in a bit. And let's say we have some kind of signal, and these are samples from some physical process, like you're sampling the wind or you're sampling some sound, noise level, or something like that over some time. And so you have a sequence of numbers A0, A1 to AN minus 1. And let's say that each of these is sampled at a time rate of delta t. So there is delta t time that has elapsed between each sample and the next sample. So let's say delta t is 0.001 second or 1 millisecond. Okay. And you compute the FFT of the sequence. So you get a sequence of complex numbers. You get capital A0, capital A1 to capital AN minus 1. And for just for simplicity, we'll divide it by n. We'll divide it by n. And let's call these the Fourier coefficients, the Fourier coefficients. Okay. Normally we don't divide by n here. We divide it on the inverse Fourier transform, but it's okay to divide by n if you want. It doesn't matter. It's up to a constant scale is all fine. All right. Now, how do we interpret this Fourier sequence? Now, the idea is each Fourier component corresponds to a frequency, and the zeroth Fourier component corresponds to zero frequency. And in fact, you can actually find out that this 1 by n a0 is just 1 by n of a0 plus a1 to an minus 1. So this is just the average value of your signal. So it's just the average of your signal. Okay, that's just the average value of your signal. And A1 through AN minus 1 correspond to various frequencies. What frequencies do they correspond to? Now, the idea is the coefficient A sub I, or 1 by n A sub I in this case, I've just decided to divide, and that's called normalizing, just dividing by n, corresponds to the coefficient frequency I by n dot this frequency of at which you're sampling. So 1 by delta t, where delta t is the time interval between two samples. So this you have to remember. So it's I divided by n dot delta t, and this is up to I equals n by 2. Let's assume n is even. So there is an n by 2 coefficient. So this is up to n by 2. All right. So we look at coefficients from a0 to a n by 2. So we look at a0, whose frequency is 0, a1, whose frequency is 1 by n, I is 1, dot 1 by delta t, a2, whose frequency is 2 by n, 1 by delta t, up to a n by 2, whose frequency is n by 2 by n, 1 by delta t. All right. Now, delta t here, let's say, is 1 millisecond, and let's say n is 1024, let's say, or let's just make it 1000. Let's just make it an even 1000. Why bother with those fancy numbers like 1024? So if n is 1000, then a1 corresponds to frequency 1 by 1000 dot 1 by 0.001, which is just 1 hertz. Remember, hertz is seconds to the power minus 1. Likewise, a2 corresponds to the frequency 2 hertz. A3 corresponds to the frequency 3 hertz. So something that goes 3 times a second. 1, 2, 3. Like 3 full oscillations per second is 3 hertz. Likewise, if you go all the way to A512, that actually corresponds to 512 hertz. Now comes the kicker. Once you go from 0, and by the way, A0 corresponds to 0 hertz. 0 hertz means that it's not oscillating, it's just constant. And that's the average. It's just constant forever. Okay. Now, these are the first 512 frequencies. And then from 513 onwards, it turns out your Fourier coefficients have a curious property. So A513 actually, so let's say A511 corresponds to 511 hertz. We interpret A513 as minus 511 hertz. And in fact, this is the strange thing that your Fourier sequence will satisfy. We can prove this, but I will not bother with a formal proof right now. Suppose you take your Fourier coefficients A0, A1 to AN by 2. Let's say n is even. And now you have AN by 2 plus 1 all the way to AN minus 1, all the way to AN minus 1. Now it turns out A1 and AN minus 1 are just conjugates of each other. Likewise, you will find out that, let me draw this properly. A0 stands by itself, A1, AN minus 1 are just complex conjugates. Now it turns out A2 and AN minus 2 are also complex conjugates of each other. So are A3 and AN minus 3 complex conjugates. And then when you go to AN by 2 minus 1 and AN by 2 plus 1, they are also complex conjugates. And then a sub n by 2, the middle Fourier coefficient, is just by itself. And in fact, you will find that this is usually a real. This has to be a real value typically. Yes. So this is very important. So you have this symmetry whenever you take an FFT of a sequence of real numbers. So whenever you take a sequence of real numbers and you take your FFT, you have this. And therefore, we interpret frequencies up to n by 2. So this is 0, this is 1 by n delta t, this is 2 by n delta t, 3 by n delta t, all the way up to here. Here you get half delta t, okay, up to this. And beyond this, we interpret these as negative frequencies, actually the minus 1 by n delta t, minus 2 by n delta t. We interpret these as negative frequencies, and we typically don't look at these because if I know these coefficients, I can predict all of these coefficients by simply taking the complex conjugate, and you get the other coefficients. We can prove this. It's actually a very easy proof, but I will not bother this proof. So therefore, if I wanted to do data analysis, the frequencies I look at are this. Now let's start with the first example. I look at weekly commodity prices. Okay. I look at weekly commodity prices and I want to look at the weekly commodity prices of some commodity. So I have those commodity prices and the time period delta T is 1 week. So I'm looking at 1 week. And let's say I look for commodity prices over 1024 weeks. So N is 1024. And I'm going to have a sequence of 1024 commodity prices for each of these weeks. And this is roughly 20 years, by the way, roughly 20 years, right? 1024 weeks. So I have my Fourier coefficients A sub 0, A sub n minus 1. I will go up to A sub 512, the middle Fourier coefficient. So this is going to be frequency 1 by 2 per week. So what I'm going to interpret it as 1 every 2 weeks. So this is going to be the middle Fourier coefficient. That's going to represent a frequency that goes once every 2 weeks. So if you have 1 week, 2 week, this signal would have done one full cycle. Whereas this frequency here, A sub 1, is once every 1024 weeks. This is twice every 1024 weeks. Likewise, let's look at the 20th coefficient. This is 20 divided by 1024 weeks. In fact, this is roughly once every 51.2 weeks, or it's going to be roughly once a year. So this frequency is roughly once a year, and likewise, right? So you have different Fourier coefficients looking at components that oscillate at different frequencies. All right. And so let's take an example. Let's actually look at a Jupyter notebook. All right, here we go. So I have posted this Jupyter notebook. I've implemented the fast Fourier transform, the inverse fast Fourier transform, and I showed you all of this. Now I downloaded weekly crude oil prices from yahoo.com. So I downloaded it from online and I just read it from a CSV file. And I take for each week the average of the opening and the closing prices. And this is how the time series looks. So this is how it looks over a span of 20 years, starting from roughly 2001 to the current date. Actually, you can see there is a dip, big dip. Guess what that's for? And then you see there is a rise here. So you can see the crude oil prices over a span of 1024 weeks, roughly 20 years. Now I take the FFT of these crude oil prices over the entire span, and I'm going to plot the frequencies, or these are complex numbers. So I'm just going to plot the absolute value of these complex numbers or the moduli. Okay. So let's see what that looks like. So if I plot the moduli of these complex numbers, so this is what it looks like. And typically we call this the spectrum. So these are the frequencies. So uh, 0 to 512, but you have to interpret these differently. So this is 0 per week, once per week, twice per week. So it goes all the way to, 1 by 1024 per week, 100 by 1024, and this is 512 by 1024. So the frequencies are important to interpret. Okay. Now, the interesting thing is you can now select the k lowest frequencies. So I wrote some code for selecting the k lowest frequency. So what does this code do? So it basically takes the DC component, which is the very first, the 0th component. It takes the first k frequencies. It fills the remainder of the Fourier series with a bunch of zeros right here, fills it with a bunch of zeros, and then it takes the mirror, the negative frequencies, the k negative frequencies. Okay, so this is important. You have to make sure that whatever FFT sequence you assemble is symmetric. So here you have FFT sequence 1 to k, and these are the conjugate. And in the middle, you have zeroed out all the remaining frequencies. So which means that you have canceled out all those components. So this gives me my way to compute a new FFT sequence. All right. And first, I'm going to look at selecting just the single lowest frequency, just the one lowest frequency. Then I compute the inverse FFT of that. And that's, let me call that sequence 1. This is the selecting the 3 lowest frequencies. Here I'm selecting the 5 lowest frequencies, the 10, 20, 40. And then I also take the difference between uh, the sequences. So let me actually show you what this looks like. So I've plotted all these things. So you can look at the lowest frequency. This is a sinusoid that will oscillate, that will complete one full oscillation over the entire 1024 weeks. As you can see, here it starts at 40, oscillates all the way up, comes back down to 40. And the reason it shifted is because of what's called the phase of the sinusoid. And that's why it shifted. So you can see how this kind of gives you a broad 20-year trend of the data, right? Over the last 20 years, if you want to tell me the story of the data, oil prices started around $40 a barrel average. They rose up to about $80 a barrel here, and then they came down. So this is like the broad trend, ignoring all the other trends. So suppose I wanted to plot the 3 lowest frequencies. So the lowest frequency is once every 20 years. The second lowest frequency is once every 10 years. And the third lowest frequency is once every 7 years. So I take the combination of all the three, and you can see how this gives you a slightly better trend that fits the data slightly better. If I took the 5 lowest frequency, you can see how I can fit the data even better. And you can see that this is smoothing the data out. This is a way of smoothing the data. Here is 10 lowest frequencies. This up to 10 lowest frequencies, you capture all the trends up to like once every 2 years, right? And you can see how this is fitting like most of the data except for some of these big fluctuations. Here are the 20 lowest frequencies, and this is like getting up to 1 year. So 1 by 20 of 20 years is 1 year. So this is getting to once per year oscillations, right? You can see it fits the data rather well. And if you subtract the black from the red, the remainders, we can call them high frequency fluctuations. So these are fluctuations that are less than once per year, that are due to frequency components, which are more than once per year, right? One or more times a year frequency components. And you can see these are the fluctuations. And you can see that using the 20 lowest frequencies, I have explained the data up to maybe plus minus $20 in the worst case. Okay, so this is interesting. Let's do the same thing for a different example. And this is a file. It's a small recording of a Bach uh, musical. So as you can hear this, hopefully you can hear this. Okay, so hopefully you heard some of that. So I can load this sound file and I can process it, and I get this is the amplitude over time, about 14 seconds. This is the total data that I have. So instead of running my own FFT, I'm going to use an FFT that's already implemented in Python in a library called NumPy. All right. So I just use that FFT. It's the same thing. And you can see here I have frequencies up to 20,000 hertz, and I have amplitude for these frequencies. Now I'm going to focus on different ranges of these frequencies. So I write some code to select from frequency range. All right. And I use that to constitute a wave file back. All right, you can read this code. I highly encourage you to read this code. Now I can select up to frequencies from 0 to 200 hertz. It's going to be very difficult for you to hear. but it's very, very difficult to hear. Let me do up to 1000 hertz. So if I constitute up to 1000 hertz, I hope you can hear the bass. Okay, it's very difficult. You have to download this yourself and run this yourself. Now I can go from 1000 to 3000 hertz, and what you will hear is the low frequencies of the violin. And if you go beyond 3000 to 15,000 hertz, what you will hear is the high frequencies from the violin, the stuff that makes the violin a little bit high frequency, the scratchy stuff. So hopefully this gives you a flavor of what people do in signal processing and why FFT is a very, very important algorithm for data analysis and for signal processing. This was very, very brief. You have to learn more. There are lots of interesting courses and books, but unfortunately, for our course, we have to stop here. Thank you and see you in the next lecture.
In this lecture, we are going to talk about a very important algorithm development technique called dynamic programming. All right. So dynamic programming is a very important class, and a lot of algorithms. For example, we will learn about shortest path algorithms in graphs, algorithms in computational biology. So these are usually take the flavor of dynamic programming algorithms. Okay. So what is dynamic programming? So dynamic programming, the programming in dynamic programming comes from a earlier word of programming, which means like it stands for more like something like scheduling or making decisions. All right. And dynamic programming as a discipline was formulated in the early 40s and the 50s for solving a class of what are called optimization problems. All right. So let me give you an example of an optimization problem that you would typically solve using dynamic programming. So the optimization problem is like this. So let's say you are a company that sells rods. Okay, so you're selling straight rods of certain length. Okay, and let's say steel rods of certain length. All right, and let's say there is a price table. So length of the rod and the price that you get for that rod. Let's say if you sell rods of length 3, you can get $1.80 for each rod. If you sell rods of length 4, you get $2 for each rod, for example. All right, and let's say that you are manufacturing rods that are of standard length capital L. So let's say L equals 10. Okay, so you're manufacturing 10-meter rods. Okay, but you can only sell 3 meters or 4 meters on the market, which means that you have to cut these rods somehow. All right, so the question is, how do I optimally cut ten-meter rods into 3 or 4 meter rods to, and this is the most important keyword, you're always maximizing or minimizing. In this case, you are maximizing. What are you maximizing? You are maximizing the price that you get. So for example, there are many options that you have when given a 10-meter rod on how you would cut it into 3 meters or 4 meter rod. So for example, here is some of the decisions you can make and the price you get for, or the payoff you get for those decisions. So for example, let's take you have 4 meters plus 4 meters And let me just remark that if you do this, then 2 meters goes to waste. Okay, so 2 meters will go to waste, but you have a 4 meter plus 4 meter rod. How much do you get for that? Well, I'll get $4. All right. How about 3 meter rods? And then here 1 meter goes to waste. How much price would you get for that? Well, you would get $1.80, so you would get $5.40. How about 2 3 meter rods and 1 4 meter rod? No waste. How much do you get? You would get 360 plus 2, you would get $5.60. All right, $5.60. All right, so here we have 3 possible choices. Let's say it's C1, C2, C3. You have more choices actually, but let's not worry about that. All right, so I have given you 3 possible choices, and among these choices, I would definitely prefer the third choice because this is among the choices I've examined, maximizing the payoff. All right, so the goal here is like this. I've given a problem, I've given you some choices you could make, and now the question is, what's the optimal choice? What's the optimal choice? What is the optimal choice? Plus, how much payoff does it give me? Okay, how much payoff does it give me? All right, is that good? So this is going to be the objective of my problem, and let's call this the rod cutting problem. All right, so one of the main ideas behind dynamic programming, and dynamic programming is based on one very key idea, and this key idea is called the optimal substructure. Okay, and this is something that we will really have to understand through the course of this week. All right, optimal substructure. Okay, and whenever you see optimal substructure in a problem, okay, and we'll have to train ourselves to see it. It's not a natural inborn talent to see optimal substructure in problems. Okay, but once you see enough examples of dynamic programming, and once you make conscious note of the optimal substructure in each of the examples you observe, let's say this week you get to observe 5 or 6 examples, and in each of the examples, let's say you make note of the optimal substructure, then it will be an idea that sinks into you, and then you are it's much easier for you then to understand optimal substructure. But let me explain in the context of this rod cutting problem. So in optimal substructure, what do we do? So first of all, we have a sequence of decisions to make. So we have a sequence of decisions, not just one decision. So even though I'm saying you can view this as making one decision 4 plus 4 or 3 plus 3 plus 3 or 3 plus 3 plus 4, let me view it as a sequence of decisions. What does it mean? So it means that given a rod of 10 centimeters, I could make my first decision whether to make a 3 meter, or I think I'm working with meters, so let me work with 10 meters. So given a rod of 10 meters, I could make a 3 meter cut or a 4 meter cut as my very first cut. Okay, 3 meters or my 4 meters. This is going to be my very first cut. All right. If I went with choice 1, if I went with 1 here, then my remaining rod is 7 meters, and I have earned myself, for making this choice, I have earned myself 180 so far. All right. If I made a 4 meter cut, then my remaining rod is 6 meters, and I have made $2 so far. All right, so this gives me the first decision I have made, 3 meters or 4 meters, and let's say I commit to this decision. Let's say I commit to this decision. For some reason, I commit to this decision. What do I have left? I have left 7 meters worth of rod, and I have left $1.80 worth of price or profit or revenue. All right, it's revenue, not profit here. All right, now what do I do? So what I am left over is the same problem as the original, but with different data. What's this different data? And the same thing here, same problem as original, but with different data. What is this different data? Well, the only data that's different is the prices still remain the same in this problem, but the only thing that's different is now I am left with 7 meters worth of rod, or I am left with 6 meters worth of rod. And now suppose I do what is the best So I do the best decision for the 6 meters. I do the best decision for the 7 meters. I do whatever is best for the 7 meters. Okay. And I can compare which one gives me better payoff. So for example, what's the best answer when you are given 7 meters of rod? Well, when you're given 7 meters of rod, you just cut it into 3 meters plus 4 meters. And that gives me $3.80. So the best here gives me $3.80. If you're given 6 meters of rod, it's very easy, cut it into 3 meters and 3 meters. So that the best here is $3.60. Okay, and now since I know that I have to do the best for the 6 meters and I get $2 already, if I go down this branch, if I go down the 4 meter branch, I know I will get $5.60. Okay, if I go down the 3 meters branch, the best I will get is 380 plus 180. I'll also get $5.60. So in this lucky instance, both the 3 meter and the 4 meter give me the same amount, which is $5.60. Okay, but let us say we went with the 4 meters. So we went with the 4 meters. So we conclude that the best decision is $5.60. That's the best payoff I get, and that payoff is obtained by committing to first cutting the rod to 4 meters and then recursively, solving the same problem for a 6 meter rod. Okay, where if you finish solving it recursively, you would find out that the best answer was to cut it into 2 rods of 3 meters, giving you a payoff of $3.60, combined with $2 gives you $5.60. All right, so we are now ready to talk more about dynamic programming and optimal substructure. So optimal substructure entails that there are 2 things that we need to do. Okay, so in the context of a problem like this, an optimization problem, what is optimal substructure? Optimal substructure says the following. So first of all, I have to make a sequence of decisions, not just a single decision. I have to make a sequence of decisions. Number 1, do I have to make a sequence of decisions in this rod cutting problem? Yes, I have to make a sequence of decisions. Number 2, if I commit to one So given where I am right now in solving the problem, if I commit to a decision, okay, if I commit to making one decision right now, then the remaining leftover problem is an instance of the original problem. This is super important. So here, if I have 10 meters of rod, my decisions are either I can cut 3 meters off or I can cut 4 meters off. Well, let me cut 4 meters off. I'm left with 6 meters of rod. Well, there's $2 of payoff for that, which I will consider, but I'm left with 6 meters, and now I have to solve a sub-problem for 6 meters worth of rod. All right? And the last and the final and the most important point as well is that the final solution involves solving step 2, this step, the subproblem in step 2 optimally, and combining with original decision. Let me illustrate this, all right. So what does it mean? If I solve this 6-meter problem optimally, well, the optimal solution for this was 3 meters, 3 meters. And then if I tack this original decision of cutting 4 meters, voila, that's the optimal for the original problem. And that contains the optimal for the subproblem. All right, so I haven't shown you yet how to solve the rod cutting problem, but what I have shown you is that I have defined this notion of an optimal substructure. What does it mean? That means 3 things. One is that the decisions you are making are sequential, which means you're making one decision after another, after another, after another, after another. So you're making a sequence of decisions. If I commit to a decision at the current stage where I am right now, if I commit to a decision, what is left over is an instance of the original problem. I have to resolve an instance of the original problem, maybe with smaller data. And finally, the final solution involves taking this little subproblem, solving it as an instance of the original problem, and combining the solution that I get for the subproblem with the decision I made to get to that subproblem. If I combine them, just like here, 3 and 3 meters is the answer to the subproblem, 4 meters is the decision I made to get to that subproblem. If I get to that, then the optimal solution looks like that. Okay? And if a problem establishes these 3, it's called having the optimal substructure property. All right. So once we have the optimal substructure property, you should think about dynamic programming. In fact, a lot of times when you have to make a sequence of decisions, you have to think about dynamic programming. And then you make a test whether the decisions can be sequenced in a way that 2 and 3 hold. And more often than not, they will hold. And you can go ahead and start to use dynamic programming. So now I'm going to talk about how do we make a dynamic programming algorithm once we have convinced ourselves that the problem has optimal substructure. Okay, I'll talk about that coming up. So now we will talk more about the rod cutting problem. So you have a rod of size L, and you have a sequence of decisions you could make. L1, which is the size of a rod you could sell for price P1. L2 is a size you could sell for size P2. And let's call it L sub n, you could sell for size P sub n. So let's call this the price table. Okay. Now my goal is to cut this rod L into some number of L1 rods plus some number of L2 rods plus some number of Ln rods plus some waste, okay, where the profit I make, or the revenue to be more precise, is N1 P1 plus N sub n P sub n. All right, so this is going to be something that I'm going to maximize revenue. It's very important to know the difference between revenue and profit. All right, so so now you have the inputs to the problem are L, the total size, and the price table. All right, and the output, you have to say what's the maximum revenue and how do I cut the rod to obtain maximum revenue. So what is max revenue attainable, and as a follow on to that, how do I attain it? In some sense, what sequence of decisions do I make to attain it? Okay, so in dynamic programming, there are many steps to solve this problem. So first step is identify, okay, identify. So let me write down the steps here. First step is identify optimal substructure. We did in the previous discussion, and the optimal substructure was like this. So if I had a rod of length L, okay, if I had a rod of length L, I could commit to one of n decisions, L1 through Ln. So those are the decisions I could commit to right now, okay. And if I committed to L1, I make an instantaneous revenue of P1 plus the sub-problem I am left with is a rod of size L minus L1. Okay. If I committed to Ln, I commit to Pn, and what is the sub-problem I am left with? A rod of size L minus Ln. So I better solve and find the answer for this sub-problem. So now we have identified the optimal substructure. I hope it's clear how we've identified the optimal substructure. It's a sequence of decisions, so you make one decision right now, and that allows you to identify the optimal substructure. Okay? So now I'm going to focus just on the first part of this problem. What is the maximum revenue attainable? So what's the maximum revenue attainable? And once I figure out what's the maximum revenue attainable, I promise we'll get to this question of how do we attain it. All right, so leave question 2 aside for now, and then let's talk about the question 1, what is the maximum revenue attainable? And so that leads us to the second step of dynamic programming, which is write down a recurrence for the optimal value. Okay, this is very important. You write down a recurrence for the optimal value, not for the sequence of decisions you get for the optimal value. What will happen, and I promise you will see this in a second, is once I get the optimal value, the sequence of decisions to get to the optimal value will also be made for me. All right, so let me write down just the recurrence for the optimal value. So in this case, let me call this optimal value function max revenue. Okay, I'm not going to write down revenue, R-E-V-E-N-U-E. I hope you can fill that out. All right, what are the inputs to it? The inputs to it are the length of the rod. All right, and that's it. That's all I need to know. Okay, the price table, I'll keep it on the side. If you wish, I could keep it as an input, but I'll just keep the price table on the side. So the maximum revenue just takes as an input the length of the rod, L. All right, now what does this recurrence look like? So it looks like this. So maximum revenue of L is going to be, so first of all, if L equals 0, okay, so if a rod has length 0, then max revenue of L is going to be 0. I can get nothing out of it. If I have nothing, I can get nothing out of it. Another point is, if L is less than 0, if a rod goes to negative length, the max revenue should be very bad. Okay, because negative length rods do not exist in physics, so I should not be giving you revenue for negative length rod. In other words, it may be the case that instead of me selling you a rod, I owe someone a rod, and that's not allowed in this problem. So I'm going to say max revenue of capital L is minus infinity, and let me put a note to revisit this. So this is the base case. All right, so what is going to be the remaining stuff? So the remaining stuff is going to be like this, right? So max revenue of L, what are the decisions I can make? So the decisions I can make are, it's going to be max of whichever is going to give me the best option of max revenue of L minus L1. So let me choose the first option and add P1 to the profit. Max of L minus L2 and let me say 0, and this is let me explain what decisions give me these. So this decision says so first decision is make a cut of size L1. Second decision is commit to a cut of size L2. And the last decision is commit to a cut size L sub n. Okay. And then I put in a 0 here. You might be wondering, why did I have to put in a 0 here? Well, the 0 is also a decision which says just waste. Okay. So this is a decision where I simply decide just to waste the rod, which means I get no revenue. So if I don't cut the rod and just throw it away as waste, I get no revenue, and that's a decision as well. Okay. So here we have all the possible decisions I can make, L1 through Ln, and one of the decisions I didn't talk about, which is waste, in which case I immediately get no revenue, I am done. All right. So now you see how the optimal substructure is reflected in this recurrence. So optimal substructure okay, optimal substructure is reflected in this recurrence. How is it reflected? It says, well, to get the maximum revenue for a rod of size L, let me try all the options I have given to me, which is cut it for size L1, for L2, L3, L4, Ln, or just waste the rod, which was a decision I should have written in this table, but it's kind of implicit in the problem, waste 0. All right, so I get no money for wasting. All right, so just waste the rod and you get 0. So these are all the decisions I'm allowed to make. If I make the decision 1, then I make an instantaneous profit of P1. I make an instantaneous profit of P1, and the leftover rod has size L minus L1. Now how do I find out what's the maximum revenue for leftover rod of size L minus L1? Well, solve the same problem, max revenue of L minus L1, and magically, hopefully, that returns the maximum revenue if I had a rod of size L minus L1, and tack on P1, and then you get the maximum revenue for L. And whichever of these options provides me the best answer is going to be the best answer for the original problem. All right. So here is the recurrence. Okay, and I can actually implement this recurrence. So let me write down for this case. I'm not going to do this for other cases. But just let me write down and convince you that, well, this is actually it, almost it. We have solved the problem, but what you will find out is if I just implemented this recurrence, it's going to be really, really bad. So define maximum revenue of L to be what? To be, first let me do the base cases. If L equals 0, return 0. If L less than 0, return minus infinity. Okay, and I'll explain to you how this minus infinity comes in a second. All right, what else? If L less than 0, and then otherwise we have to just do each of these options. So it's going to be for L sub I, price sub I, in table, in my price table. Okay, I'm doing it in Python like notation. Compute max revenue equals max of max revenue okay, comma P sub I plus max rev of L minus L sub I. So, and then let me give it a different name. Let me call it max so far, and initialize max so far at the beginning to be 0. Why is that? Because I'm allowed to say it's max of 0 comma, so I'll initialize it to be 0, and this implements, this for loop implements this series of max. The 0 is the initial value, okay, and return max so far. That's the recurrence for max revenue. Now the problem is, I invite you to run this recurrence. What you will find out is that this recurrence is going to be really, really bad. Okay, so we'll have to do something about how to speed this recurrence up. So this, if you just implement this recurrence, it solves this first problem. What is the max revenue attainable? You do solve it, but it's going to be really, really bad in terms of running time, because each max revenue of L is going to come up with so many different sub-problems of max revenue L. And one thing I'll convince you is that you're going to do a lot of repeated work. So you're going to do a lot of, especially in this step, you're going to do a lot of repeated work. And let me convince you that you're going to do a lot of repeated work coming right up, all right, by examining this recurrence slightly in more detail. Now we are going to talk about step 3. Step 1, identify optimal substructure. Step 2, write down a recurrence for the optimal value. This recurrence has a name. That's a technical name that I've been avoiding so far. But if people mention this name, don't be confused. This is what they're talking about. This is called the value function. And sometimes it's called the optimal cost to go. Okay, so cost to go. Let me try and fit that, cost to go. Okay, and I have to mention this, that dynamic programming is actually more than an algorithm design technique. Okay, it's used heavily in other areas of engineering. So one area where it's used is an area called optimal control. Okay, so for example, controlling chemical plants, controlling reactors in chemical plants, controlling aircrafts, all of it is sometimes done using dynamic programming. Even path planning for robots, like if you have a self-driving car, how do you navigate and plan a path? And there are algorithms for it based on dynamic programming. So it's more than just a thing for solving rod cutting problems. Okay, it's a very, very deep subject. Let me also mention the name Bellman. Okay, so Bellman was a mathematician who in the 50s and 40s invented and pioneered this technique of dynamic programming. All right, just a couple of side notes. I would feel very bad not mentioning this, so I just mentioned it. All right, so where are we so far? So we've gone through the first 2 steps, and for the rod cutting problem, we have written down the maximum revenue for a rod of size L. That's 0 if the rod is of length 0. That's minus infinity, and I'm going to talk about this minus infinity a little bit. So take my word for it that this is sensible, and we will see exactly why in a second. And then you have this main recurrence. So these are the base cases, and then there's the main recurrence which says it's the maximum of 0, and 0 is the solution where you waste. This is for choosing option L1 with price P1. This is for choosing option Ln with price Pn. And you see, for each option you have a remaining subproblem remaining subproblem, and the payoff from choosing this option. And that's going to be the total payoff for the original rod of size L. Very good. Now, if you directly implement this recurrence, it does solve this problem, but it's going to be very expensive. So let's take an example to see why it's expensive. Let's take back to the original example we started off the whole thing with. So L equals 10, and then the price table is just two things. If you L1 equals 3, L2 equals 4, $1.80, and $2. Okay, so that was the what we decided to go with. All right, so now we have an original rod of size 10. So we are starting the whole problem. Okay, so we are starting the whole problem with max revenue of size 10. Well, if you look through this recursion, the base case doesn't apply. So what applies is it's going to be the max of two things: max revenue of 7 plus 180, or max revenue of 6 plus 2. Okay, n equals 2, so there's just two branches of this recursion. All right. So what about max revenue of 7? So let me write this as a tree because it's much easier to view the recursion tree, and the space in the board goes downward. So forgive me for a second while I reconsider my bad decision to write it left to right. Let me write it top down. So max revenue of 10 is either the max of either of it. So it's going to be max revenue of 10 minus 3 is 7 plus 1.8, or max revenue 6 plus 2. Whichever one is bigger is going to give me the answer at the top. Now what about max revenue of 7? Well, max revenue of 7, again the recursion applies to max revenue of 7, and so you get it's the max of max revenue of 4 plus 1.8, or it's going to be the max revenue of 3 plus 2. All right. Now what about max revenue of 4 plus 1.8? Well, that's going to be max of there's always 0 here. There's always 0 here. Okay. There's always 0 option here, which I'm not going to write down. I hope you keep it in mind. So it's the max of 0, this and this, max of 0, this and this. All right. So it's going to be the max of 0, max revenue. It's getting tiring already, right? 1 plus 1.8, max revenue of 0 plus 2. Okay, very good. Now what about max revenue of 1 plus 1.8? Well, this is going to be max of 0, max revenue of 1 minus 3 is minus 2 plus 1.8, or max revenue of minus 3 plus 2. Okay. Now here is where I really have to consider negative values of length. So if you are wondering right at the beginning, why should I even bother with negative values of length? This is why, because my algorithm doesn't know that negative rods make no sense. When I program a recursion like this, expect the value, the argument of this recursion to go negative. If it's going negative, you have to interpret what's happening. So let us interpret what's happening. I have been left with a rod of size 1, and when I have been left with a rod of size 1, I cannot cut it to a rod of negative size. So I cannot take a rod of size 1, cut off a rod of size 3, and be left over with a rod of size minus 2. Well, I can inside a computer, but not in real life. So this is nonsense. So this part is going to nonsense. So I need to cut this off, and the way to cut this off is by saying that if I get to negative, it is really, really, really bad. And how do I say really, really, really bad to someone who is trying to maximize their revenue? Well, give them a revenue of minus infinity. Minus infinity, if you are trying to be a businessman, business person, and you want to maximize your revenue as a business person, well, if I gave you minus infinity revenue as a business person, that's like saying game over. So this is one way of doing it, and therefore, whenever you get to minus 2 here, the base case hits. So this becomes minus infinity. This becomes minus infinity. So the base case starts to hit. All right. So this becomes minus infinity. And the whole thing is max of 0, minus infinity, minus infinity. So therefore, I have to replace this whole thing after the computation by 0. So the best option here is to waste. If I have a rod of length 1, the best option is to waste. And likewise, what happens here, and so this is 0, what happens here, so this is max revenue of 0 plus 2, max revenue of 0 is replaced by 0, so this is 2. And this was max revenue of 1 plus 1.8, so this whole thing gets replaced by 1.8. So therefore, this part, max revenue of 4, the best value is 2. So this part gets replaced by 3.8. Likewise, what's max revenue of 3? Well, if you did the math, then max revenue of 3 will come out to be 1.8. So this gives me a 3.8. So now you can see how this recurrence is working. All right, what happens on the other branch? So now I get max revenue of 6. So when I get max revenue of 6, what happens? I'm going to compute, it's going to be the max between 0, max revenue of 3 plus 1.8, max revenue of 2 plus 2. Now the problem here is you can already see the problem. I have already tackled max revenue of 3 beforehand. Now I'm going to recompute it. I have already tackled max revenue of 2 on this branch. Now I'm going to recompute it. So what's happening is terms like max revenue of 3 are getting computed multiple times. And that's bad. Okay? So if terms like max revenue of 3 are getting computed multiple times, what you're going to have to end up doing is, well, I'm going to have to really worry about computing max revenue of 3, max revenue of 3, max revenue of 3. But every time I call max revenue of 3, the answer is the same. So if only I could remember, if I could have remembered that max revenue of 3 was 1.8 from before, then whenever I re-encountered max revenue of 3, I don't even need to go into the guts of this whole recurrence. All I need to do is I need to recognize that I have seen it before, and I need to just fill in the value. So the third part of dynamic programming, therefore, is to memorize. And if I don't memorize, what happens is I end up repeating the same amount of work again and again and again and again. So I better know how to memorize. All right, so that's going to be the third important step of dynamic programming. Okay, and memorization here is going to be, so people use memorization using hash tables. All right, one of the issues we have with hash tables is they are okay. In practice, they are fine, but one of the issues is you will never get to guarantee a complexity bound with hash tables, because the worst case, if you're interested in worst case, the worst case for hash tables can be quite bad. All right, so therefore what we will do is we will build a memo table that we will design ourselves. Okay, now what is this memo table? So this memo table is going to be how I am going to cache the results. All right, so let me assume for simplicity that L is a natural number and lengths L1 through Ln are all natural numbers. Okay, so if I'm going to start with max revenue of capital L as my first recurrence, then the kind of arguments that I will have are all going to be lengths of the form between L, L minus 1, all the way up to 0. And then let me have, remember on the side that if it's negative, then it's minus infinity. All right, so I'm going to have this memo table T, capital T. Okay, so once I have this memo table for max revenue, then the algorithm becomes very, very simple. What am I going to do? Well, I will start the memo table on the left at 0 with 0. So this is going to be different from my pseudocode convention. This memo table is going to start from 0 and go all the way to capital L. Okay, so it's going to be a different table. And what am I going to say? Well, t of 0 is going to be 0 for I equals 1 to L. What do I do? Well, I simply implement this recurrence, but instead of wherever I see max revenue, just look up the memo table. So what is happening? T of I equals max of 0 T of I minus L1 plus P1 T of I minus Ln plus Pn. And remember, if I index t with a negative value, make sure that you return minus infinity. So I'm not going to write down that logic, that code that you need to implement that in using an array. You obviously cannot index an array with a negative number. So you'll have to do something here as an if statement or something to implement this. I'm not going to do that right here. But instead of calling a recurrence, here you're just looking up a value. And the nice thing is you're going to fill this array from the right all the way to the left. And so when I'm filling up t of I, all of these are already filled up. So I fill it up all the way until I get to t of L. Okay, so this is a much more elegant way of filling it up using a memo table than by using a recurrence. All right, so we are done with the third step of dynamic programming. So what's the third step? So first step, identify the optimal substructure, write down a recurrence. Third step is memowise. And memowise is the super important step where you are going to make a table, design a way of filling up the table. And here it's really simple. I designed a table. I noted that at the 0th entry of the table is 0. Everything below 0, the negative entries of the table, I don't have to write them down. They are all minus infinity because of the base case. So I make sure about that. For I equals 1 to L, so I'm going to iterate through the table from 1 to L. T of I is just implement this recurrence, except that every time I want to call back the recursive function, just look up the memo table. Okay, instead of calling an entire recurrence, I just look up the memo table. And once I have implemented all of this, T sub L, T of L is going to be the max revenue attainable for a rod of length L. Okay, so I am done with computing this. So this is the first step, computing the value function. So now I have to get to the very last step of dynamic programming, recover the solution. So let me tell you how I am going to recover the solution. All right, and that's coming up right now. All right, see you then. So now we are back to the last step, which is recovering the solution. So let me also work out how the dynamic programming solution works out for capital L equals 10. Okay, so for L equals 10, I have a memo table, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, all right, and then anything negative is minus infinity. All right, with that in mind, with this recurrence, I'm going to implement this algorithm. So what will happen is I'm going to start filling from 1 to L. So when I fill out T1, so T1 is going to simply be max of 0, T minus 2 plus 1.8, T minus 3 plus 2, just expanding this, and that's simply going to be minus infinity, minus infinity. So this is going to be also 0. What about T2? T2 is going to be very, very similar story. You can make sure that it's going to be 0. T3 is going to be max of 0, T0 plus 1.8, t minus 1 plus 2. Now this is going to be minus infinity, and this is going to be t0 is already 0, so this is going to be 1.8, this is going to be minus infinity, so the max is going to be 1.8. T of 4 is going to be max of 0, t of 0 plus 2, t of 1 plus 1.8. Now all of these values are known, so we can fill it up. So this is going to be 2, this is going to be 1.8, so the best option is 2, so this is going to be 2. All right, so we are going to fill up this table like this. All right, now the main thing here is how do I recover the solution as I am filling it up. So let me write down a different table called the S table. As I am writing down the T table, let me write down a S table that's going to annotate the decision that's giving me the best solution. So not only the optimal cost to go or the value function, but I'm also going to store the decision that got me there. What does that mean? Well, for t of 0, let me simply say the decision is nil. There is no decision to make, so that's nil. For t of 1, the decision is the way I got there, the best decision was to waste. Okay? For t of 2, the best decision was to waste. For t of 3, the best decision came out to be to cut a rod of size 3. So I'm going to record that and say cut a rod of size 3. For t of 4, the best decision was to cut a rod of size 4. So now I'm going to declare what is the best decision. So one of the decisions here I didn't write down is the waste decision, which is going to give you nothing. All right. So I'm going to have to annotate this decision. So what about t of 5? So t of 5 is max 0, t of 2 plus 1.8, t of 1 plus 2. So the best answer is going to become this, which is 2, 1.8. So the best answer is 2. So for 5, the best answer is 2. And the best decision is to cut a rod of length 4. For 6, the best answer is going to become, take my word for it, 3.6. Okay, and the best decision is to cut a rod of size 3. What does this best decision say? The best decision says what's the decision I should do right now? What's the best decision locally? So this is not the best decision globally, this is the best decision so far for right now. Because we are staging the decision one after another, we can say what's the best decision right now. Okay, and likewise for t of 10, the best answer is going to become 5.6, and the best decision, it's going to be a tie, but you can always choose the best decision, is to choose to cut for length 4. All right, so now that I have the best decision, all right, so now that I have filled up the S table and the T table, how do I recover the solution? Well, to recover the solution for 10, let me look up S of 10, and that says the best decision is to cut for size 4. So when I cut for size 4, then I get to length 6. The best decision for that is to cut for size 3. When I get to size 3, the next decision is length 3. Then I get to size 3, then the next decision is 0. I don't have to say nil, but this is going to be how I recover my solution. So how do I recover my solution then? To recover the solution, not only do I, when I have a max of 3 terms, not only do I say what is the maximum value, on a side table remember which choice led me to that maximum value right now. So what's the immediate choice I made to get to the maximum value? And when I represented this immediate choice somehow in a different table, and I filled out the memo table T, and likewise as I fill out T, I fill out S, I can now recover the series of cuts that I need to make by traversing S after I am done. How do I do that? Let me start at S of 10 because the original size is 10. It tells me to cut down to a rod of size 4. So the remaining rod size is 6. So let me look up S of 6. That tells me to cut a rod of size 3. Remaining rod size is 6 minus 3, 3. That tells me to cut a rod of size 3. Remaining rod size is 0. So this is how I recover the decision. So to recover the solution, record the immediate decision that gave you currently the maximum value, and then once I get to the end of the memo table, read it off by looking at the S table sequentially. All right. I hope this is clear. I will post the code for this, but I also challenge you, encourage you to think about how are you going to code up this algorithm, how can we improve the way we code up this algorithm, and so on. All right. So now I'm going to show you more examples of dynamic programming so that we can see this pattern repeat again and again and again. Okay, see you there. Okay, so now we are going to look at dynamic programming for a different problem called the coin changing problem. So what's this idea? Every time you visit a supermarket and you give them more money, let's say you buy items worth for $18.10 and you give $20, then you receive change for $1.90. All right, and typically this change is made up by $1 plus 50 cents plus 25 cents plus 10 cents plus 5 cents. All right, so you will get some coins back, and this is how you are given change. All right, so now the question is, how do I make change optimally? So in other words, suppose I'm given a bunch of denominations. So I'm given a bunch of coins, and let's say I'm only given 20-cent coins, 25-cent coins, and 5-cent coins. All right, so I'm only given 20, 25, and 5-cent coins, and I need to make change for let's say 40 cents. Okay, and I need to do so by minimizing the number of coins. Okay, I want to make change by minimizing the number of coins used because I don't want to give you too many coins, load you up with a lot of coins. I just want to give you change with the minimum number of coins possible, given that I only have 20 cent, 25 cent, and 5 cents. Okay, so how do I do this? So first of all, if you look at this, then there are multiple options for doing this. So if I want to make 40 cents, I can give you 8 5-cent coins. Okay, and the number of coins I've used is 8. If I could give you 25 cent plus 3 5-cent coins, and the number of coins I've used is 4, even better. Or I can give you 2 20-cent coins, and the number of coins I've used is 2. So the best solution is to give you 2 20-cent coins, and we are done. All right. Now, how do I calculate this kind of best solution given what are the inputs to the problem? So I'm given a bunch of coins. So I have 20 cents, 25 cents, 5 cents. So I'm given some coins, C1, C2, C3, up to Cn. So I'm given some denominations for these coins. I'm given a target amount, T, to make change. So choose what is the decision I'm making, N1 C1 cent coins plus N Cn cent coins, okay, N sub n, such that the total denomination equals T. So I cannot give you change for more than T. I should not give you change for less than T. I shouldn't overcharge you or I shouldn't undercharge you, okay. and minimize, in doing so, minimize the total number of coins. That's the number of coins I'm using, so minimize that. All right. Hopefully this is clear. This is the problem. Now let us follow these 4 steps to actually solve this problem. All right. And while doing so, I'm going to show you 2 different ways of following these 4 steps. Okay, they are kind of different in very trivial senses, but in any case I will show you 2 different ways. So this is actually somewhat similar to the rod cutting problem. So we can use a lot of inspiration from the rod cutting problem, because there you had a target length of rod, you had some lengths that you were allowed to cut, and you wanted to line up some of these lengths to be as close as possible to the target length. You're allowed to waste, but you're not allowed to overshoot. Okay, here you're not allowed to waste, so wasting is not an option. All right, let's ID the optimal substructure. So suppose I had 40 cents, t equals 40 cents. All right, now let me make the decision right now on which coin to choose. So I can either choose a 20-cent coin, I can choose a 25-cent coin, or I can choose a 5-cent coin. So once I've committed to a decision to choose a 20-cent coin, what is remaining? The remaining amount T1 is 20 cents. Okay, so whatever the optimal way of making change for 20 cents, to that if I add 1 coin, that gives me the answer from the branch where I have committed to 20 cents. What about the branch where I have committed to 5 cents? Well, the remaining amount is 15 cents. So now I am committed to making change for 15 cents in an optimal fashion. Okay, I am committed to making 15-cent change in an optimal fashion. And to that, if I add 1 more coin to account for the fact that I have already chosen a 25-cent coin. And likewise, here the remaining amount is 35 cents. So I'm committed to making change for 35 cents now. To that, if I add the 1 coin to account for 5-cent coin, then I have gotten the change for 40 cents. So what is the optimal substructure? Well, first of all, it's a sequence of decisions. I need to decide what coin to give you first, then another coin, then another coin. So it's a sequence of coins that I am deciding to give to you. All right. Now, once I have decided the first member of the sequence, what is left over is an instance of the original problem with different data. This different data is a different amount for which I have to give you change. And I have to make into account the fact that I've already used up a coin to get to 20 cents. I have used up a 20-cent coin. So I add that because the number of coins is what I'm minimizing. So the overall solution is going to be the minimum of these 3 options. All right. I hope this optimal substructure is clear in this problem. So if it is clear, let's write down a recurrence min coins for a given target amount t. Okay. Now this recurrence is going to have some base cases. So one of the base cases is the easy base case when the target amount is 0. If the target amount is 0, how many coins do I need to give you change for 0 cents? Well, the answer is always 0. That's great. All right. Very good. Now there's going to be another base case where the target amount is less than 0. How do we ever get to a situation where the target amount is less than 0? Well, we get to a situation where if I have given you change for more than the original target amount, I will get to a remaining target that's less than 0. Okay, we already saw this situation in the rod cutting example previously. And here, this is a very undesirable situation, very undesirable. So what do I do with a very undesirable situation? Well, I have to give it a very undesirable value. Okay, but in this case, I am minimizing the number of coins. In the previous case, remember in the rod cutting, I was maximizing my revenue. Here I am minimizing the number of coins. So if you are minimizing the number of coins, if you are minimizing, let's say, the cost, what is the worst cost I can give you when you are minimizing? Well, the answer is plus infinity. So in this case, it's going to be plus infinity is the base case when I have overshot my original target. So you have to understand when this case t less than 0 occurs during the solving of the problem and what should be the value given for it. The rest of it is just going to be a recurrence that reflects the optimal substructure. So what's the optimal substructure? Well, it's the minimum of the options that I have. So what's the option that I have? Well, I can choose a coin, and now it's going to be min coins of t minus c sub 1, 1 plus min coins of t minus c sub 2, 1 plus min coins of t minus c sub n. So whichever one gives me the minimum, add 1, and that's the answer for the original problem. So this is the recursive case, and this gives me the recurrence. So with this recurrence, step 2 is done, all right. And now step 3 is going to be very, very simple. So what is step 3? So in step 3, I take this recurrence and I design a memo table. The memo table for this is going to be very similar to the memo table for the rod cutting problem. All right, so here, since I've already used t as the target, let me use TBL for the table. Okay, so in this memo table, I start with the target amount t, 0 up to the original amount capital T, and then here I have for 0 it's 0, if it's less than 0 it's minus infinity, and now I'm going to fill the memo table for I equals 1 to my original target amount t, TBL of I equals min of 1 plus TBL of I minus C1, 1 plus TBL of I minus C sub n. So implement this logic here and make sure that if it ever goes less than 0, it has to be given a value of minus infinity. All right, and now how do I recover my original solution? Okay, very, very simple. Add an extra table called S that's going to, for each amount, tell me what is the coin, or it's going to be nil, what's the coin that I need to do to get to the optimal solution for right now. Okay, just like we did for the rod cutting problem, and that is obtained by recording at each step which of these cases gave me the minimum, and corresponding to that I would say S of I equals j. If the jth coin gave me the minimum, then I will put S of I equals j. All right, and with that I can simply solve the coin changing problem. So if you know how to solve the rod cutting problem, you could solve a very, very similar problem, but instead of maximizing in the rod cutting, you are minimizing in the coin changing. Also, instead of allowing you to waste, you are not allowed to waste. But even in spite of all those differences, if you follow this formula, what you get is the same kind of solution, a very similar looking solution with some key differences. But what dynamic programming comes down to is when you identify a recurrence for the optimal value, the rest of it just becomes kind of automatic. So in this lecture, we are going to study a problem called the knapsack problem. Okay, so the knapsack is an important problem, but we have a very, like many algorithms, this comes with a very funny formulation. So imagine there is a thief, okay, and imagine that the thief has a knapsack, and the knapsack is there to have the stolen goods, all right, but the knapsack has a weight capacity W. So W is the weight capacity of the knapsack, which means that whatever goods are stored inside this knapsack, the sum of the weights of the goods has to be less than or equal to W, and if it's more than W, then the entire sack tears and all the stuff is left on the floor and the thief cannot steal anything. All right, so what are the options for the thief? Well, the thief has a bunch of items that the thief can steal. So item 1, the weight of the item is W1, and the value, the dollar value of the item is V1. Item 2, weight is W2, the dollar value is V2. Item n, weight is Wn, dollar value is V sub n. All right. So these are the items and their weights. So their weights and the dollar values. All right. Now, being a greedy thief,